Okay, so let me play the interaction video, and after that, the session can start.
Okay, Mikael, should we get started?
Sure. The video was a little quiet, but the chair is yours.
Yeah. Sorry, I didn't get what you said. Okay. First of all, I'm afraid of putting on my video because okay. First of all, let me welcome all of you to this second session of this parallel about detector for future facilities, R&D and novel techniques. We will have 15 talks today, which span a very broad range of detectors, from pixelated detector, resistive plate detector, micromegas, liquid argon satellites, and a very broad, equally broad range of application, from accelerator physics, neutrino, dark matter, space science. I remind you that talks are 12 minutes. We have 3 additional minutes for questions. I will advise you 2 minutes before the end of your talk, and I ask the speaker to stick, if possible, to the 12 minutes. The session is quite packed, and so we need to try to stay in our time. So the first talk is from Eric Kagan from Ohio State University for the RD42 collaboration, and will talk us about new beam test result of 3D pixel detector constructed with polysilicon diamond. Please, Harris, share your screen and start your.
Okay, may I begin?
Sure.
Okay, can you see my screen? Seems to be.
Yes, I can see your screen. Please go.
Let me just go a little bit lower in size, and no, it's not going to fit. Okay, well, I'll do it like this.
I mean, for me, it's fine on both sides. I mean, this is a bit small. If you can go to a bigger one, it's better. But...
yeah, it's not working, so I'm just going to leave it like this.
That's fine. That's fine. Please go on.
Okay, so I'm going to talk about 3D pixel detectors constructed with polycrystalline CVD diamond. The outline of my talk is here. There's an introduction and something about diamond detectors. That's mostly just a review. And then I will show the beam test results of the 3D pixel detectors with the diamond, summarize, and future plans. Okay, so what is the motivation for this? Well, the next generation of inner tracking detectors will certainly have to be able to withstand somewhere in the 10 to the 16th to 10 to the 17th hadrons per square centimeter, and rates from, say, gigahertz to hundreds of gigahertz per square centimeter. Current detectors might survive a short time at the HL-LHC, and so this has spurred an enormous amount of R&D for more tolerant detector designs and or materials. So the talk that I'm giving is about diamond as a material. some of the properties are the radiation tolerance, and William Tristock will be the next talk, and he'll show the results on radiation tolerance. Diamond is an insulating material, high charge carrier mobility, etc. And so it has many good properties, but it also has the one property which means, or the feature which gives most of the good properties, which is the large band gap, also gives smaller signals than silicon in the same thickness as silicon. And that, of course, just has to do with the band gap. So RD42 is the group that did most of this work, and we investigate various detector designs, pads, strips, pixels. What I'm talking about is 3D detectors, and specifically 3D detectors read out with pixel detector electronics. And of course, this is aimed at a design to reduce the drift distance and make them even more, have the loss of charge due to irradiation even less, so that we can reach to 10 to the 17th hadrons per square centimeter. Okay. So this is the RD42 collaboration. I'm not going to spend any time on it. It's been going on for quite some time, and it's a relatively stable collaboration. Okay, so how does Diamond work as a particle detector? Well, Diamond detectors are basically operated as ionization chambers. That's the figure here. In other words, you have a bulk piece of diamond, a certain thickness. You have metallization on both sides. A charged particle goes through, you create electron hole pairs, and then you sweep the charge out. There's no ion implantation, etc. The material I'm talking about today, and is used for most detectors in experiments, is polycrystalline material, and it comes in wafers just like silicon. A wafer is shown here, a 15 centimeter diameter wafer. This is as grown. You can't see through it. It has a rough surface. It has to be processed to go from a rough wafer into a detector. And then we get the material, we prepare it to turn it into a detector. We put metallization on both sides, and we've done, as I said earlier, pads, strips. This talk is about pixels, and then we connect it either by wire bond or bump bonded. So the picture on the lower right is actually a polycrystalline diamond. It's now clear because it's polished. You can see through it. It has a 3D pixel detector on it, and it's bump bonded to an Atlas front end diaphragm. I'm going to show the results from this one. You can see the wire bonds, you can see the pixel chip underneath it, and you can see what the diamond looks like after processing. Okay. So why are we interested in 3D devices? Well, after large radiation fluence, all detectors are trap limited. Let me say that again. All detectors are trap limited. And so the way to think about this is you have a mean free path, or a Schupfweg, which is then less than 50 microns. And so if you can keep the drift much smaller than the Schupfweg, than lambda, then you can collect a sizable fraction of charge. If you cannot, then you're going to lose a sizable fraction of charge. So in the comparison of planar and 3D, which is shown here, they both have the same thickness, which is called delta here. The drift in a planar detector would essentially be the thickness L, but you can see that if you can make a 3D detector, which has these columns coming through the device from one face to the other, then you can determine the drift distance to be essentially anything that you want. So 3D geometry increases the collected charge in detectors with limited Schupfweg, or mean free path. But the 3D geometry, because of the inherent nature, which I'm going to talk about next, introduces low electric field regions, which could be a problem. So this is a picture of some TCAD simulations, which we use to compare with measurements. This is the cells we started with, 150 by 150, 150 microns by 150 micron cells. The voltage applied is 25 volts. The black dots are the readout. The whitish open circles are the field wires. And what you can see is these red areas in between the field areas on the edges are these low field regions that I talk about, the saddle points. And So we ran the simulation, but indeed simulations indicate that if we can adjust the column diameters and the spacing with the present technology, then 3D pixel devices should work well enough to test. And so it's an issue of, can we produce the devices with the required specifications? Okay, so how do we make these devices? Well, we make them with a femtosecond laser, 800 nanometers. And basically, if you focus a high-powered laser into a diamond material, you can convert the insulating diamond into a resistive mixture of various carbon phases. There's amorphous carbon, diamond-like carbon, nano diamond, and graphite. This picture on the bottom sort of shows what we actually do is we have a bulk diamond. We have the laser coming from the top. The laser goes through the diamond. Remember, I said the diamond is clear. So the laser can go through the diamond. We focus at the backside, and then we don't move the laser beam. We move the diamond vertically, thereby drawing this column of amorphous carbon, diamond-like carbon, nano diamond, and graphite through the material until we get to the other side. And then we've created an electrode. So this is a non-trivial methodology. Initial methods, we had a 90% column yield. We're now at about greater than 99% yield. And the key that made that was a thing called spatial light modulation. In other words, adjust the laser beam for what has to happen when it goes through the diamond material. Our initial columns were like in silicon, 6 to 10 microns. We're now down at 2.6 microns with SLM. And to get to 10 to the 17th, we will be making columns under 2 microns, about 1.6, 1.7 microns in diameter. Okay, so what are the successes that we've had, just so you get a feeling? I think we've already published results that prove that 3D works in polycrystalline material. We scaled up the number of cells from 100 to 4,000. That's the scale that I'm going to be showing today. We reduced the size from 150 by 50 down to 50 by 50. Again, I'm going to be showing that today. And in the next year, we'll be down at 25 by 25 micron cells. We've reduced the column diameter from 6 to 10 microns to 2.6. Again, I'll be showing that today. In the future, we'll be at 1 to 2 microns. We've increased the column yield from 90% to 99%. And most recently, we tested the first 50 by 50 micron 3D device irradiated to 3.5 times 10 to the 15th, 800 MeV protons per square centimeter. I'm not going to show those results today. That analysis is still ongoing. And there's small, that is less than 10% loss of charge in this device, which is pretty spectacular for where we need to be at this point. Visible improvements have occurred at each device, and the measurements are consistent with the TCAD predictions to first order. I mean, there are always details which you have to get right. Okay, so let me go to spend the second half of the talk showing you results. So this is a picture of the surface of the device. This is a device with this, which is read out by CMS Pixel Electronics. This is the picture on the left shows what we did to make the device. The diamond is at the bottom, the readout electronics is on top. And because the readout electronics is based on 150 by 100 micron cells, we ganged 6 cells. This is the ganging on top. You can see the holes where we connect to the columns. You can see the bump bonds. And then this picture here showing the black line shows each of the square cells, which are made up into one ganging. We use surface metallization to do the ganging. We ganged in this device 6 cells, 3 by 2. This was bumped together with indium bumps on both the ASIC and the detector. And what's shown in the picture is that there's a small gap, about a 15 micron gap. The columns do not go all the way through.
Harris, you have 2 minutes left.
Yeah, the columns do not go all the way through, but they have about a 15 micron gap. And then this is the same device in Atlas. It's now ganged because Atlas is 50 by 250, front end I4. It's ganged 5 cells in a row. And again, we show the ganging and the bump bonds. Everything else is identical. The 2 devices were made with the same technology. So what are the results from CMS? This is basically the efficiency as a function of position. You can see in the maroon, we had a bump bonding issue. We had some surface issues, which we knew ahead of time. The device had about a 99.2% efficiency. We expected 99.6, and the high voltage curve of the efficiency is shown on the right. Everything above 15 volts, we're at the plateau. We then took that test was done at PSI, where there's lots of multiple scattering. We went to a CERN test beam. Of course, it's a high energy beam, and you can now see that the clarity of the results. We can see individual issues, etc. We got the same efficiency, 99.2. If we then go to the Atlas device, things are very, very similar. This was the first tin silver solder bumps instead of indium. It's again done at CERN. We have about 3 micron resolution. We got about 98.2%, and the inefficiencies are most likely due to processing that you can see on the surface picture here. The plateau is very reasonable. We didn't map the whole plateau. We just didn't have time. And then this is the time over threshold distribution. So the pulse height, where we used a gain of 5 TOT, is about 11,000 electrons. And so we had a mean TOT of 6.73, which is about 14,800 electrons, about twice the charge we would get from a normal planar polycrystalline material. And we're still calibrating the low TOT bins, which...
Harry, sorry to interrupt you. You should try to wrap up your talk.
I'm wrapping it up right now.
Great.
So here's the summary. There's been lots of progress. I've talked about each of these things, what we've succeeded. We've scaled the devices down in size. There's been visible improvements at each step. The efficiencies look good. There's still, of course, things to be understood. Simulation needs some effort because it's complicated and takes a lot of time. But all the devices we produce work to first order as expected. What are our future plans? We will continue irradiating the 50 by 50 device. We have data at 3.5 times 10 to the 15th, 800 MeV protons per square centimeters. We'll continue to 10 to the 16th this year. We'll be at 10 to the 17th next year. We'll be at 25 by 25 micron pixel detectors, and we hope to be able to read this out with an RD53 chip in the next year. Then we'll continue scaling up so that we can make devices that are usable in experiments, expand the facilities, and begin, hopefully, production for the Atlas BCM Prime, which will use one of these pixel detectors, or will use 3D polycrystalline pixels as part of its device. Thank you.
Thank you, Aris, for a very nice talk, very clear. We have 1 minute and a half for questions. Please use the raise hand tool to ask, to make a question to the speaker. Okay.
I didn't understand that, so.
Please use, I was saying to use the raise hand tool to make questions to the speaker.
Oh, okay. So let me stop sharing. Well,
yes, I see that Michal raised his hand.
Okay, that's fine.
Okay, so this is Michal Marszowski from Prague. I have a quick question. So I see there has been progress in the area. You have a very nice and interesting result. So I'm familiar with silicon, not with diamond. So what are the typical biasing voltages and breakdown voltages for your sensors? And I have a question, since it's a very wide band gap semiconductor and you have a very thin columns, is it possible in principle to have a charge multiplication?
The answer is, okay, let me start. So the voltages are shown on the plots. They're there. We typically go from 0 volts to 80 or 90 volts in the test that we did. So at that range, we have no trouble at all. I think the highest voltage that we've taken these devices to is something like 120 or 130 volts. So we have a little bit of headroom on the top. We haven't tried to make the voltage higher. I think I alluded to this, but there is certainly, since this is a catastrophic process making these columns, we certainly would have expected to be able to go to higher voltages without things going wrong. We haven't succeeded in that regard yet. We don't exactly, it's one of the things we don't exactly understand, but we're working on it. And then in terms of charge multiplication, I think if you look at charge multiplication in silicon and do the appropriate scaling, you have to have a very large electric field for that to happen. We haven't seen charge multiplication yet in these devices. There is a paper that we've written on charge multiplication in diamond, and it's a very, very interesting concept. But what we would do is not necessarily make the columns small enough. We actually would probably go the other way, but we could put in the material a focusing ring in the bulk of the diamond. We've succeeded in doing that. We haven't succeeded in getting multiplication by this, but all the simulations show that if we put a focusing ring in the bulk of the material, we should be able to reach a level of multiplication in the diamond. Did I answer your questions?
Yes, thank you.
Okay, I think we need to move on. We don't have time for more questions. We go to the next speaker. Again, for the RD42 collaboration, William Trishuk from University of Toronto, who will talk us about the latest result on radiation tolerance of CVD diamond sensors. So it's closely linked to the previous talk. So please, William, go on. William, please start. You can start your talk.
Mute. Can you hear me now?
Yes, now we can.
Okay, and you can see my slides?
Yes.
Okay, I'm going to just go ahead and not make them full screen because I had problems with my microphone while I was doing this. So I'm going to tell you a little bit about latest results on radiation tolerance of CVD diamonds. I won't spend any more time on the author list. This is all done by the RD42 collaboration, just as Harris was talking about previously. And as he mentioned, diamonds in a MIP sensor is really just a solid state ionization device. And what we're going to be worried about here with radiation hardness is the introduction of traps in the volume that stops the charges. So charges drift across under the influence of an electric field. They don't necessarily have to reach the electrode to produce a signal. Any charges that stop will induce a signal on the electrode and contribute to the overall readout. And so that's what we're going to be studying, is how far they drift, or what the mean free path of drift is. This just shows, just to remind you how we test these things. This is our standard candle for understanding the radiation tolerance in diamond detectors. This is a 5x5 millimeter single crystal diamond in this case. So I'll show you both poly and single crystal diamonds and the results that follow. It's read out by a very slow 2 microsecond shaping time Lepura readout electronics that charge sensitive amplifiers. And you can see there's 128 channels there, but typically we make a 64 channel device, and we can reuse these readouts 4 times because there are backup bond pads and things. So we can test things several times, but every point that I'm going to show you is typically an irradiated diamond and then it's attached to the electronics that hasn't been irradiated, put in a test beam. So it's 2 or 3 weeks work, and then we take the sample and irradiate it further and bring it back to another test beam a few months later. So you have to make one of these for every single point that I'm going to show you and what follows. Just to show you some of the raw data, this is in single crystal diamonds. The blue histograms are unirradiated single crystal diamond. You can see we have 15,000 charges. That's the limit of the band gap in an ideal diamond. And then 6 radiation doses reduce the signal either for positive high voltage or negative high voltage. The signals are very similar, as you can see. And we still have a viable signal down to in excess of 10 to the 16 at the bottom there. The most probable signal is still 3,000 or 4,000 charges. And we have readouts that we've used on those. This particular examples are for 800 MeV proton irradiations, but I'll show you the various species in a few minutes. The mean free path in diamond is, of course, is what we're going to try to, as I say, what we're going to try to measure to characterize the effect of the introduction of traps, so how much radiation tolerance or damage has been induced. You only get all of the charge if the mean free path becomes infinite. On the right here, you can see if the mean free path over the thickness is 10, you still only collect 95% of the charge. So you have to get to 100 or 1,000 to get all of it. When diamond produced very little signal, the mean free path was linearly proportional to the signal, the charge collected. And so we sort of thought of them interchangeably 10 or 15 years ago, but now we're clearly up into better quality material where we need to understand the full characteristic curve. This is the full formula for the relationship between the total charge collected as proportional to the thickness relative to the mean free path. And of course, the mean free path could be different for electrons and holes. It's likely not as different as it is in silicon. The carrier lifetimes are only 30% difference as opposed to a factor of 3 3 different in silicon. And so we explore, we don't really know what the difference in mean free path could be between electrons and holes. The radiation produces traps that pin down or stop electrons and holes. But we explore a range of options around 1.3. Which is the ratio of the lifetimes. And you can see it doesn't make much difference in this relationship. So we're going to take all the charges that we measure and convert them to the charges that we measure on the y-axis here and convert them to mean free paths on the x-axis in what follows. And we use 1.3 as the way we do that conversion. But you can see there's a few percent discrepancy if holes or electrons are getting unexpectedly more trapped than the lifetime ratio would suggest. So what happens when we irradiate things? The radiation induces traps in the material. It shortens the mean free path. And so 1 over the mean free path goes down proportional, or the mean free path goes down, 1 over the mean free path goes up proportional to the fluence phi and proportional to some damage constant that might be different for protons, neutrons, and different energies of protons and so on. And this is the simple proportionality that we expect to see. And indeed, when you go through and measure about 15 different samples in this plot, the 2 points typically that you can see here together are for positive and negative voltage. So you can see there's some difference at bias voltage on the sample. You can see there's some difference, but it's small. They're small compared to most of the effects that we measure here. In this plot, there are irradiations of both single crystal diamonds in the solid points. They tend to be down here at the very large. The very small 1 over lambdas, the very large lambdas to start, and they get a little bit smaller lambdas as they get irradiated out here, or the polycrystalline diamonds, which you see in open points tend to have larger lambdas to start with. There are some traps in the polycrystalline diamond that we characterize by 1 over lambda 0. But in terms of these different species, they're all linear, but they have different damage constants K. And so we can go through and actually determine what those slopes of those lines are. And then we can turn it around and say, well, what if I made the slopes all the same? Neutrons are a little over 4 times as damaging as protons, 70 MeV protons 2.5 times, 800 MeV protons about 70% more damaging than protons. But you can use these scaling factors to drop all those lines on top of each other. And then you can plot all of the points, single crystal in solid points, polycrystal in open points. Sometimes it's hard to see the open points when they're all clustered together here, into a universal damage curve for the mean free path versus collection distance. And of course, we didn't irradiate neutrons out to almost 10 to the 17, but they're multiplied by 4 here. They were irradiated out to 15 or 16, 10 to the 15, and then multiplied by a scaling factor of 4. You can also do that in linear space in 1 over lambda space, and you get a nice straight line. And you can see the sort of deviation from these lines. There are a few points that are 10 or 15 or 20% away, but basically everything else falls on this universal curve. What's actually going on inside the diamond? You can actually have a look and see in polycrystalline diamond, it's not a matter of the whole diamond changing, but in fact, the unirradiated samples, this is examples from a proton, 24 GeV proton irradiation. There are hotspots that have 2 or 3 times as much charge as the average or the typical value. But as you irradiate it, those hotspots actually go away. We kept this on the same scale, so the average goes down by a factor of 5 from left to right here. But what you can see is that the spread is narrowing. And so if we plot the spread of these points, so down at the bottom here is a histogram of the 500 roughly pixels that are in each of these plots. And these are the different charges with respect to the average one. And as you irradiate it, of course, the average goes down, and that doesn't show up in these plots, but the spread narrows. And so we characterize this by the full width half maximum over the most probable that I'll show you in the next slide. But we expect that because if you rearrange this lambda versus phi relationship and differentiate it, d lambda d phi is proportional to minus lambda squared. So the best stuff, the stuff that had the largest lambda to start with, is going to damage fastest, and it's actually quadratic according to this simple prediction. And that's sort of what we see in polycrystalline diamond. The hotspots get damped out, and the energy resolution or the spread in charges that we see drops down. In single crystal, there is no preferred place. This all has the same charge average, and so it's roughly constant. So this is an interesting property of this irradiation and kind of what's going on in the micro level inside the diamond. In the last couple of minutes, I'm just going to say a few words about high rates in diamonds. So we go to the PSI test beam where we can get 10, 20 megahertz per square centimeter. We can't get the gigahertz per square centimeter that the LHC needs, and we're looking forward to more intense test beams to be able to follow this up further. To understand what's going on in the diamond, in these pad detectors, we put a CMS pixel telescope because we're going to have multiple tracks going through this at the same time. And we want to be able to track them independently and efficiently and know when we have 2 or 7 tracks going through at the same time. Unfortunately, at 300 MeV pions in the PSI setup, we're limited by multiple scatterings. So you get 20 or 30 micron precision, but we put relatively large pads over the whole area of those diamonds I showed you. So now we're not doing strips or pixels on the diamonds. It's just one pad of 4 millimeters on a side. If the diamond is 5 millimeters on a side, or 8 millimeters, the pads on a 1 centimeter diamond. We read them out at 2 gigasamples per second. And so this is what the raw data looks like for 20 triggers when we have beams going through at 10 megahertz per square centimeter. This is where we trigger, and in those 20 triggers, there are 20 pulses. The diamond is 100% efficient, but you can see there's also 20 other particles, roughly on average 1, somewhere within 500 nanoseconds of our trigger. So you get pile up, you get other particles going by. And what we're trying to understand is whether this pile up is building up charge in the diamond and likely to change the pulse height of the event that we triggered on. You can go even further than 20, of course, then you can do 5,000 of these things and you can start to see quite clearly our trigger pulse. Again, there's, roughly within 99.9%, 5,000 triggers here, but you can see the bunch structure of the PSI beam every 20 nanoseconds. There's the possibility that more particles spill out of the cyclotron at PSI. And we're trying to look and see how is that affecting the pulse height at the peak that we're testing. And so these are the results for neutron irradiated polycrystalline diamond. We've done it for proton diamond as well. So there's a similar set of plots. The top lines are for fluent 0 unirradiated diamond, for negative bias voltage, and for positive bias voltage to see if that
William, 2 minutes left.
Good, no problem. See if that makes any difference. And you can see this is a very suppressed scale. These are all normalized to the average. So these 6 points average to 1 by definition. And there's sort of 1, 2, maybe 3% variations across the range of fluences from 10 hertz or so. We can get the beam down to up to 10 megahertz on a good day or on an average day. And there are some points at 20 megahertz here. So between 10 and 20 megahertz is where we've been able to explore reliably. And again, each one of these scans is a whole test beam, because then we have to go away and make another sample at slightly more irradiated and another sample. And then next year we do this one, and the year after that we do this one. So there's a lot of work that goes into calibrating these things from year to year and from sample to sample and cross-checking things. We also study whether it matters whether you start at low rate and go to high rate, or whether you start at high rate and go to low rate. I believe these ones were actually done at random. So we've done all those different things to see whether there are any effects on that. But all of these things are flat to better than 2%. Up to 10 or 20 megahertz, as I say. This one didn't actually make it past 1 megahertz or 2 megahertz that year, but because we couldn't get the collimator set up. And we've been exploring systematics at the order of 1% to try to understand, there's people's eyes pick out different things in all these things. Do they all bend over? Do they curve up or curve down? But this is going to turn out to be a few percent independent. So the average pulse height is independent of the exposure. Again, up to 20 megahertz, as Harris said, at the HL-LHC, we're talking about gigahertz. So we're looking forward to getting to 100 megahertz or higher at a certain test beam when things come back in the next year or so. So I think I'll just summarize with that. Diamond sensors have a long history of applications in HEP. There are a number of diamonds that have been in the LHC for 8 years and show no sign of chronic dose doing anything. All of these things are sort of acute doses. We dose them in a week or a month, and then we see how they behave. But we've dosed things now over 8 years at the LHC, not up to 10 to the 16 yet, but at least as far as we've gotten at the LHC, things look consistent with our acute dose tests. Signals remain viable up to 10 to the 16. I showed you a number of points like that in the early part of the talk, and MIP signals are stable up to fluxes of 10 or 20 megahertz, depending on how far we were able to get in any of those given tests. Harris told you a little bit about how we can get a little bit more or a lot more charge out of these things in 3D devices. And Marco yesterday told people about the next generation of beam conditions monitors, which will rely on all of these things, because we will get to 10 to the 16 in the next few years. So I think I'll stop there.
Thank you, William. We have time for 1 or 2 questions. Please raise your hand to make question to the speaker. I I don't see. Okay, there is Mikael. Please,
yes,
go.
Again from me. So this looks quite impressive in terms of results. Can you comment on the annealing? How does the diamonds anneal compared to silicon, and what are the microscopic mechanisms?
Yeah, so we have saved all of these diamonds, and as I implied, many of them have gone back 2 or 3 years later. We don't do anything special to store them, so they're all stored at room temperature. They're all operated at room temperature, and we haven't seen any gross changes in the properties of these things. So I think there's neither beneficial nor degradative annealing observed. But we have done studies where we've tried to heat things up and see if we can improve them. But again, the band gap is so large that these temperature effects and the defects that we're making in them seem to be immobile at the sort of typical temperatures one would access in a normal experiment.
Have you tried making a single point damage, let's say with cobalt-60? We
have done photon irradiations with cobalt sources but single point, I'm not sure what you mean by that.
That the electron is only to kick out only one of the carbon atoms from the silicon lattice. That is different from neutrons, which produce clusters from primary carbon atoms.
I'm not sure that the cobalt photons are capable of doing that. The binding energy of diamonds is so much higher than you're used to in silicon. That's what gives it its radiation tolerance.
Yeah, but still, it's about, I don't know, 20 electron volts in silicon, and you need something like 250 kilo electron volt electron or photon to kick it out.
Yeah. So as I say, all I can say is we have done photon irradiations with an intense cobalt source, and we don't actually show these because we haven't observed any change in the behavior of the signal with those photon sources out to hundreds of megarads.
That's very interesting. Thank you.
Okay. I don't see any other rise at the end, so we can move on to the next speaker, who is Paolo Yengo from CERN. Will talk us about the development and test of a micropattern resistive plate detector. Please, Paolo, go and share your screen.
Hello, can you hear me?
Yes, perfectly.
Okay, I'm trying to share. Do you see my slides?
I can see your slides. Please go
on. Okay, good afternoon, everybody. So we move from silicon to gas detectors now, and I will show you development and actually the first construction of a preliminary test of structures based on micropattern detectors by micropattern technique to be used as a resistive plate detectors. So a few introductory words. The rate capability of resistive plate detectors, RPC, depends on a number of factors, and among them by the resistivity of the plates. The development of resistive plate detectors with low resistivity is actually one of the most interesting research lines in the recent years in order to extend the rate capability of these devices to higher rate to be used for upgrades of current detectors and for future apparatus. So here you see how the rate capability depends on the bulk resistivity, on the average charge, and on the total thickness. It is essentially inversely proportional to these three quantities. And one can play on each of these three in order to increase the rate capability. This is a plot from RPC, glass RPC, showing the rate capability measured as a function of the conductance of the plate. So you see how it scales. So clearly one option is to reduce the resistivity of the plates in order to get a device that can stand higher rate capabilities. But there are a number of drawbacks to this way. Here, what I present is a first attempt of building an RPC-like detector with a technique that is nowadays used for a number of gas detectors that are grouped in the family of micropattern detectors, like GEMS, Micromegas, Micro and Airwell, and number of others. The MPGD community is actually a very live community, and there are a number of new detectors that are coming every year. A step forward in this development, this family of detector was obtained a few years ago with the development in the context of the Atlas project of the resistive protection of micromegas in order to suppress the discharge intensity in the detector to allow the use of this device in a large experiments, which is now the case for Atlas project. The MPGD detectors are often used as a tracking device in applications where particle rate is not sustainable for wide chambers or more traditional detectors. And this is the case, for example, of the upgrade of the muon system of Atlas and CMS. The single layer time resolution is limited to order of few or several nanoseconds on these devices when we consider the gas behavior. So here the aim of this little study is to reach performance in terms of time resolution, which are similar to the one of the standard phenolic Menalvin RPCs, and which is able to efficiently work at particle rates of order of 100 kilohertz per centimeter square and beyond. So let's come now to the detector layout, which is indeed inspired by the micromegas for the Atlas detector. The first prototype was built at CERN. It is composed by two equal plates electrodes. There is a substrate of FR4, which is 2 millimeters thick, on which there are resistive, copper strips for the readout. On top of this substrate, there is a Kapton layer glued, which is carrying the resistive protection, which is patterned in as a strip. So the strip pitch, the readout strip pitch is 400 microns and the width is 300 microns. The resistive lines have essentially the same width and the same pitch. So matching the one of the readout strips. High voltage is directly applied on the resistive strips. The connection between the resistive layer and the high voltage is done through the Kapton with via filled with silver-based epoxy paste. In total, the detector, each plate has 250 readout strips for each view. And the two plates are equal, essentially, and they are separated by a 2 millimeter gap and are rotated by 90 degrees with respect to each other in order to provide two-dimensional tracking capabilities. Finally, to keep the distance of the 2 millimeters between the two plates, we used a frame with a cross in the middle made of FR4. Now, FR4 is not the best material to prevent sparking, so it was then protected with Kapton. As it is a resistive device, the first thing is the characterization of the resistive layer. Resistive strips are produced by screen printing on top of Kapton foil using a 100 kilo ohm polymer resistor, which is in form of paste. The strips have a cross section which is D-shaped, so they are not flat, with a maximum height of ranging between 15 and 20 microns. And they are interconnected in pairs every centimeter, as you see here. So there is this ladder structure, which allow to have a more uniform distribution of the high voltage. The Kapton foil on which the resistive strips are printed is then glued on top of the substrate by applying high voltage, high pressure, and high temperature. At the end of this process, a mechanical polishing procedure is performed on top of the resistive strips in order to flatten them down and to remove possible small bumps in the structure, and in order to provide a better stability of the working point. Still on the characterization of the resistive layers, the obtained resistive of the two plates was pretty good and pretty uniform, as you see here, on the order of 5 to 10 megaohm per square. So here you see the 2D map of the resistance for the two plates. Okay, here is a picture, a sketch of the detector, which is equipped with the two readout connector. And here there's the high voltage input line to provide high voltage to the resistive part. The two bottom plot shows the measurement of the resistance on one of the plate. The left plot shows the resistance measured starting from these sides, but at a constant distance between two probes. So essentially, you see that the resistance is pretty much stable. This plot can be seen as a slicing of the top plots for the 2D map. On the other hand, if you measure the resistance with the, let's say, from the high voltage input line and moving along this direction, so along the X direction in the figure, you see a linear increase of the resistance, which is essentially expected because of the structure of the detector. So let's now, before moving on, compare. Let's say or highlight the main difference of this device with the traditional RPC. The first difference is in the concept of the protection on the resistive protection, because in the RPC, what matters is the bulk resistivity of the plates. The conductive electrodes are on the outside of the resistive plates. This is a sketch from a CMS RPC. You apply high voltage on the outside, and the charge carriers they go through the bulk of the material. So this is why what matters is the bulk.
Paolo, you have 2 minutes left.
Yes. In our case, there is only surface resistivity that matters because the carriers move along the strips. These also imply a difference in the voltage drop. In one case, it's uniform. In our case, it is it increases along X. As I said, the charge carriers are different. They are positive in the ions in case for the RPC. In our case, they are electrons. And there are also some technical differences in order to smooth down the flatness, or to improve the flatness of the plates. Possible advantages of our system is that we can control the surface resistivity by selecting or tuning the resistive paste. We have a thin separation between resistive electrodes and copper readout strips, allowing a good induction of the signal, so we have a higher signal. We reduce the charge spread in the precision coordinate, which can help in going to high rate applications. So preliminary tests have been done at CERN by using standard RPC gas mixtures. The detector showed quite high instabilities in terms of high voltage correlated to local defects of the surface. However, we could measure the good efficiency of the device. So this means that optimization are needed for this detector. For this, we think, for example, to improve the flatness of the resistive protection, also using other way of treating the surface. So in conclusion, we have built a resistive parallel plate detector with micropattern techniques. It potentially offers several advantages to be used as a trigger device in high rate environments. Preliminary results are encouraging. However, performance studies are ongoing and a number of improvements are already considered, as first of all, optimization of the resistive layer in order to cope with the observed instability. Thank you very much.
Thank you, Paolo. Thank you for the very clear talk. We have time for 1 or 2 questions. Please raise hand if you want to make question to the speakers, to the speaker. I don't see raise hands. Let me ask a very naive question. What are the plans to cure this instability that you observed in the test you have performed and you have shown in the last
yes.
one of the last slides?
First of all, is to double check the gas that was used, because I mean this was a mixture that was done on the spot. Test was very quick. Then there is the, let's say, a number of as I mentioned here, treatment of the resistive surface. There are let's say mechanical ways that can be used to have a better to smooth down a little unevenness of the surface. Those are procedures that are standard for production of printed circuit boards, and that are also used in other detectors like the Atlas Micromegas. So a review of this of the surface is needed. Additional possible use of chemicals like the one used in the RPC. I mean, the RPC used the linseed oil in order to create a very thin layer on top of the plates to smooth down little bumps. And this is something that I plan to also to use in this device. So there are several ways to test.
Okay, there are several handles to improve this instability.
Yeah.
Thank you, Paolo. I don't see raised hands, so we can move on to the next speaker, who is Maria Teresa Camerlingo from University of Rome 3 and INFN plus CERN. She will talk us about small pad resistive micromega rate capability for different spark protection resistance schemes. Please go on, Maria Teresa, share your screen and start your talk.
Okay. Do you see my slides?
Yes, I
Okay.
can see your slide. Please go on.
Okay. Hello, everybody. This presentation is about some result of the R&D studies on small pad resistive micromegas detector for high rate application of more than 10 megahertz over square centimeter. It consists in a brief introduction on micromegas technology up to the presented prototype. So a description of the spark suppression resistive layout and comparison of detector performance. I finally report the result of the studies on the rate capability and spark probability. A micromegas detector is a planar proportional mode micropattern gaseous detector. It means that X signal is proportional to the energy lost by particle interacting by gas. As visible from the picture, its active volume is divided into 2 gaps by a micromesh. It separates the region of signal conversion in which there is a no-zero drift electric field that avoids the recombination of the electron-ion pairs, and the region of the signal amplification in which the electric field is enough intense to allow the electron avalanche multiplication phenomenon with using a relative low voltage difference between the micromesh and the anode plane. Thanks to the small dimension of the amplification gap that are around 120 microns. However, this gap is vulnerable to discharge, and so it was added a layer of resistive strip capacitative coupled with the redout strip as spark suppression resistive layout, as described by Paolo in his slide 4 and 5. So I don't go further. Since the current high energy physics experiment look toward high intensity collision, our R&D aims to develop a new generation of resistive micromegas detector able to efficiently operate at 10 megahertz over square centimeter particle rate. And the mandatory choice was to the miniaturization of the redout electrodes to lower their occupancy. The previous strip of 20 square millimeter area were replaced by a few millimeter pads. So a new spark suppression resistive layout is necessary to match this new geometry, and so the R&D project is centered on the optimization of this resistive layout. All the actual small pad micromegas prototypes have a small dimension and a common anode plane reported in the slide, with already a conspicuous number of electronics channels. Two different spark suppression resistive layouts were implemented and compared. In this slide, the scheme 1 is reported, and it is called the pad pattern embedded resistor schemes, or shortly PAD-P. It consists in 2 layers of resistive pad in the black in the figure that overlay the readout pad in yellow. As you can see, all the pads of each column are interconnected by an intermediate embedded resistor or bias that evacuates the current from the resistive pad to the ground. The pad detector has a very spatial resolution as visible in the red box, a moderate energy resolution in the green box, and the PAD-P gain factor is affected by charging up due to the exposed the electric component alongside the amplification gap that are the light blue part of the sketch of the layout. And its effects are visible in the time trend of the current reporting in the purple box when a source is put close to the detector. Even if these not outstanding values, PAD-P has a very stable behavior, and it is robust against discharge, as reported in the next slide 11. To overcome the limitation of the scheme 1 and to follow the general interest on the diamond-like carbon application in micropattern gaseous detector, in the second proposed scheme, the 2 segmented plane were replaced by 2 continuous DLC foils. Thanks to that, as visible from the picture reported in the slide, the spatial resolution improves because there is a large spread of charge above the pads, as well as the energy resolution improves thanks to a electric field configuration more uniform, and due to the coverage of the electric part alongside the amplification gap, also the charging gap effect is minimized as visible from the current in the purple box. However, in this layout, the full coverage of low resistance vias is not perfect, as visible from the picture at the left. And this and uncovered vias leads increase of the discharge probability. So the precision of the alignment and of the coverage of the vias was improved in the most recent building procedure called the sequential build-up technique that uses a different kind of DLC foils that is easier to deal. So the standard DLC and this view DLC prototype are a quite large family, and the specific feature of each DLC prototype are reported in this slide. I just want to point out that the DLC resistivity of the couple of the SBU prototype are too low for the rate range of interest, but we included them in the following studies. In this slide, there is the relative gain respect to its value at low rate as a function of rate per several amplification voltages for pad P and DLC20 as the best representative of the DLC family. To reach the low value of rate, we used an iron 55 source, and after we switched to an X-ray gun for the high value, fixing the irradiated area. And the first thing that we observed was that pad P required a higher amplification voltage to reach the same gain factor of DLC prototypes. And you can see from the range of rate lower than 0.5 megahertz of a square centimeter that the gain drop in pad P is already severely affected by the charging gap contribution that it saturates around 20 megahertz of a square centimeter as visible in the plot at the bottom. While DLC in the low rate range has a quite stable trend. We set as a limit on the acceptable rate capability 20% of gain drop. So as you can see from the plot on the full rate range of X-ray, both the layout are valid candidate up to 20 megahertz of a square centimeter when the amplification voltage for pad P is lower than
Maria Teresa, you have 2 minutes left, sorry.
Okay, and for DLC, an amplification voltage lower than 510. We repeated the same studies varying the irradiated area. It's visible that pad P is independent from the irradiated area, while DLC become independent when the irradiated area is much larger than the unit cell defined by the vias pitch. These detectors, together with the SBU couple, were tested in PyMu1 beam facility with a 300 MeV charge and pion beam. The detected rate in our setup position was a few kilohertz over square centimeter. That was too low to repeat the studies on rate capability. So we did preliminary discharge studies. on this detector. We reproduced the gain curve for the tested detector to use this curve to the second plot in which there is a spark probability as a function of the gain. As already anticipated, for high gain value, PAD-P is the most robust prototypes, and the gain curve are in agreement with the reference curve measured at the lab. In conclusion, for application of 10 megahertz per square centimeter, the pad geometry, the pad readout geometry required new spark suppression resistive layout. Two different layouts were implemented and compared. The results are summarized in this slide, but the general comment is that the PAD-P detector showed the best performance in terms of robustness of the detector, while the DLC prototype show better tracking performance. Therefore, both the layout are suitable candidate for be the resistive layout according to the specific application. Thanks for your attention.
Thank you, Maria Teresa. Other question for Maria Teresa? Please raise your hand. I don't see raised hand. Let me ask. I have a curiosity. I saw in one of your first slide that the distance of the micromesh from the anode plate was 128 micrometers.
Yes.
It looks to me something very finely tuned. How well do you need to control this distance and the other ones that you show in your device, and how critical is it for the correct operation of the device?
Okay, it's not so precise. Indeed, we usually say that it's almost 120 microns, especially for the small dimension prototype in which they use the bulk technique. We can have variation of few microns on the height of the amplification gap, but obviously it works on the intensity of amplification electric field, but with the amplification voltage, you can tune the electric field even if the height of the amplification gap can change. So we used to do calibration curve about the gain factor and which better amplification voltage we need to use even if the height of gap amplification gap is can vary about a few microns with the bulk technique.
Okay, thank you. It was clear. So it's not that critical.
No.
As I imagine. Okay, I don't see
it's
any
just
other.
The picture, the user picture that put the nominal length.
Okay, thank you. I don't see any other raised hand, so we can move on. We can go to the next speaker, who is Elisabeth Ross-Sterling from the Université Libre de Bruxelles, on behalf of the CMS Muon Group. She will talk us about electrical discharge mitigation strategy for future CMS jump system GE21 and ME0. Please. I can see your slide and I can hear your voice, so please go on.
Okay, perfect. So just to start off with, to talk about the the technology that's being used here, we use GEM, gas electron multiplier detectors. They're a kind of micropattern gas detector. Their main components are a printed circuit readout board. In the case of triple GEM detectors, 3 polyimide or Kapton foils with 50 micrometer holes that are chemically etched into them, and a drift cathode board, as well as additional components such as protective chimney, cooling pipe, GEM electronics board, and the front end electronics that go on it, as well as inner and outer structural frames. So the main layers are sealed within a gas type volume. The gas that's used differs depending on your needs, but in the case of CMS GEMs, we use 70% argon and 30% CO2. We apply a high voltage to the foils, and this creates an electric field inside the holes like you see in the bottom left image. And so ionizing particles such as muons will enter the detector and they'll ionize the gas within. And then these primary ionized electrons will experience a Townsend avalanche at each foil layer's amplification region. Gain differs depending on the gas and the settings that you use, but typically you get a gain of about 10 to the 4. So these are being placed inside the compact muon solenoids muon NCAP. We're adding 3 new GEM-based systems. Right now during LS2, we are adding GE11 in front of the ME11 CSCs, cathode strip chambers. In extended year-end technical stop 2023-24, we are adding GE21, which is going to go in front of the ME21 CSCs. And finally, in long shutdown 3 in 2025-27, we'll be adding ME0, which is our very forward muon tagger. Now, I would love to tell you all about GE11, but in the interest of time, I'm going to have to point you to Giovanni's talk Friday at 8:30 in the morning. So please, it's really interesting. Go see it. In the meantime, I'm going to talk about the future systems that we're more interested in. So GE21 consists of 18 staggered superchambers per NCAP, and a superchamber is 2 detectors coupled with each other. Each of these detectors is 4 modules with 12 readout sectors each. We have about 440,000 readout channels. So this is the same amount of readout channels as we have with GE11, but each chamber spans 20 degrees, so twice as much as GE11. You can see the size differences in the image on the bottom left corner. One of the really interesting things about GE21, since we have extra time to develop them, is we've really been able to fix up the electronics. So we have these plug-in cards for our VFAT3 front-end readout chips. So they're made of a flexible portion and a rigid portion. The flexible portion is nice because this can absorb any residual misalignment between the GEM electronics board and the readout board. But more importantly to this talk is the rigid portion. So this allows us to put an improved protection circuit that was too large for the original readout hybrid. So the hybrid that we use for GE11 is in the center. And you can see I've pointed out that in front of the inputs to the Panasonic connector, we have this array of resistors. But because our space was so limited, we were very limited in what kind of resistors, what kind of protection circuit we could use. This plug-in card gives us more physical area to work with so we can try different circuits. ME0, on the other hand, this is our very forward muon tagger. So this is also 18 staggered stacks per NCAP, but instead of being 2 chambers, it's 6 chambers in a single stack superchamber. They also span 20 degrees. But rather being 4 modules, they're a single module. And we have about 650,000 readout channels that comes with ME0. So here's the problem. So for GE11, we had a 2-year demonstrator system called the slice test. And during the life of the slice test, a significant portion of our readout channels were lost. And you can see that in the graph on the right. And so the cause of this was we had propagating electrical discharges within the detector, which could cause damage to the readout channel inputs on the VFAT hybrids. And you can see that in the picture on the left. You see that the solder's been melted, some of the silicon gets ablated away. It just causes a whole lot of damage. Now, unfortunately, in large triple GEM detectors like GE11, GE21, the discharge propagation within them is a lot more complex than for smaller detectors. So you always have your discharges that begin on GEM3, the 3rd foil in the stack, because this is where the Rather limit can be exceeded. You can actually have a discharge. But the problem is these discharges can actually propagate backwards up the stack before moving forward again towards the readout electronics. And each time they propagate backwards or forwards, they're gaining more energy and becoming more dangerous to the readout. And what's worse is that these discharge propagations can actually reignite if given enough energy. So I want to talk about 2 different mitigation strategies we're currently looking at for GE21 and ME0. And the first of these is the protection circuits. So in order to test any different protection circuits we had interest in, we took a GE11 detector and we populated the narrow end with the absolute baseline VFAT hybrid. So this doesn't have the additional protection resistors that you saw on the GE11 hybrid. It's nothing except the internal protection that clearly wasn't good enough for preventing the damage. We had an R&D plugin card that we used. We put it in between the JEB and the VFATs, and this way we could insert the different protection circuits that we want to test. We used cosmic muons for this test, and our trigger signal was provided by a coincidence between two scintillator paddles, like you see in the image. So we looked at a couple different kinds of protection circuits. We had a resistor-only circuit, and this was intended to mimic what we have with GE11. This lets us test any resistor arrays that were considered too big for the hybrid that may be better than those. It also lets us do a cross-check of the protection under harsher conditions than we were able to check. A second kind of circuit is resistors and diodes. And so this kind of circuit is intended to prevent damage to the VFAT3 in the event of a propagating discharge. Now, on the other hand, we have the resistor and capacitance circuits. And so this is intended to prevent those discharges from propagating in the first place. It won't prevent damage if a discharge actually does propagate. But as we say in English, an ounce of prevention is worth a pound of cure. So we want to try to stop these in the first place. So looking at the RNC protection circuits, we wanted to look at the efficiency of the detectors if these circuits affected the detector efficiency. And so we calculated this efficiency as a ratio between the number of events with at least one hit and the total number of triggered events. We saw that systematic error from electronic noise didn't really play a large role until that threshold surpassed 50 kilohertz. And when we look at this in total, we see that really no efficiency loss was observed with the addition of this circuit. Actually, we see that in this case, the efficiency was slightly higher with the RNC circuit than it was without it. This is likely just due to the fact that we had an improved grounding scheme, but still the results look really positive. Some of you may notice that the efficiency is around 75 to 80%. Now, of course, this is much lower than the ideal of 97, but we're not concerned about this. There's a couple reasons that really went into this that don't have to do with the circuit itself. So taking that into account, the ratio between the circuit and not the circuit is really promising, as you can see here on the right. So this is something that we're currently looking into. We're continuing to try different circuits, but so far things are looking really good. So our second mitigation strategy is double segmented foils. So for GE11, we use single segmented foils. And what that means is that the top of each gem foil was partitioned into these 100 square centimeter HV segments. And each of these sectors had a 10 mega ohm protection resistor that was soldered directly onto the foil. But the bottom of the foils wasn't segmented like this. It was a single continuous conductor. And the problem with this is that a large conductor the size of a gem detector that we're using in CMS has a very high capacitance. And that means there's a large store of energy available to the propagating discharges. And as you can see in this plot, that gets problematic really quickly. And so this mitigation strategy, we're going to segment the bottom of the gem foils in the same way that we segmented the top. So same size, also 100 square centimeters. We put 100 kilo ohm resistors between the sectors on the bottom to act as decoupling resistors. This particular value was chosen just because it gives a good ratio between the top and the bottom resistors. That way the potential on the bottom doesn't jump to the top and cause a discharge in the exact opposite that we want it to do. So what we saw was that the double segmentation of the foils reduces the probability of discharge propagation in a GE11 detector to a significant degree. We're talking even greater than just for a little 100 square centimeter detector. And at the nominal CMS induction field of 4 kilovolts per centimeter, the propagation probability is virtually zero. And this is down from 70% from a GE11 detector. So this is really, really impressive. But if it's so impressive, why am I talking about it? So the double segmentation introduced a new problem. So it introduced this crosstalk signal where VFATs that were along the same HV partition would see this spurious signal that wasn't related to any source particle. And so if you look at the figure on the left, I've put a source on VFAT 0, and VFATs 8 and 16 are within the same HV sector. And so in the S-curves on the right, you see at VFAT 0, you see the signal from the source as you would expect. But then also in VFATs 8 and 16, you see this baseline of signal that should not be there. And so that's our crosstalk signal. And the cause of this, if you look here, So I have a source and I radiate it towards readout sector A, so VFAT 0, and I get the signal that you see on the right in pink. Unfortunately, this signal is mirrored in the next readout sector B, along the same HV partition. And so we get this opposite polarity signal in green. And so if the amplitude of this negative tail of the reflected signal is high enough.
Elizabeth, you have 2 minutes left.
Okay, cool. I'm gonna go really fast then. If the amplitude is high enough that it's gonna register as actual signal, and that's a problem. We've done a bunch of simulations and found that this can lead to a maximum efficiency loss of about 6% for the Z to mu channels. So this is very not ideal. So we did some studies. We wanted to study the effect of the size of these bottom HV partitions. And so we took a double segmented GE11 and we modified it to go from 100 square centimeter segments to a 900 square centimeter segment. We used americium-241 as a source of highly ionizing particles through a hole in the drift around VFAT 0, and then took SPIT scans to assess the amount and location of the crosstalk. So for those of you who may not be familiar with it, SPITs are a cluster data format for the trigger, and a rate scan will show us the SPIT rate as a function of the global threshold. So if you look at the example plot on the right, the peak in the scan to the left of 50 data acquisition DAC units is noise, and anything to the right of 50 is signal. So without any kind of source present, the signal is going to be cosmic ray muons. And with a source present, this is going to be either true signal or crosstalk, depending on what VFAT you're looking at. And so this was the results of that study. So the top plots are with the fine segmentation, the 100 square centimeters, and the bottom plots are with that 900 square centimeters. And what we do see is that we see a large amplitude reduction of this crosstalk signal, about 2 times reduction going from 100 to 900 square centimeters. But of course, the problem is this brings us back to the original issue of having a large induction capacity. So right now, the potential solution that we're looking into is to utilize double segmentations on foils 1 and 2, but not for the third foil. And so in order to make this cost efficient, so we can use the same mask when we are producing the foils, what we're going to do is use 0 ohm resistors to connect the segments on the bottom of G3 to make it act as if it's a single continuous conductor, but it's made the same way as the other foils. Investigations are still ongoing. All of our results, as you know, got delayed by coronavirus. So I can't show you what we have right now, but I will tell you that the results look really, really promising. So this solution is probably what we're going to end up going with. And so in conclusion, and I'm pretty sure I'm mostly in time, is that discharge damage mitigation is a top priority for our future GEM systems, GE21 and ME0. GE21 utilizes a new Flex PCB plug-in card that lets us use more robust protection circuits. In particular, we're focusing on an RNC circuit as a promising way to reduce the propagation probability in the first place without affecting detector efficiency. And finally, the double segmentation of GEM foils reduces the discharge propagation at the cost of introducing that crosstalk signal. We do need more experimentation, but so far results look promising. So thank you to everyone who contributed to these results. I've got some references if you want to read more about it. And any questions?
Thank you, Elizabeth. Question for the speakers, I don't see any raised hand.
Cool.
Yes, there is Paolo. Please go on.
Yeah, I actually have 2 questions. I don't know if I am allowed. The first one is more on the topic.
If they are short, yes.
Yeah. Okay. The first one is more on the topic about this segmentation. When you add this 10 mega ohm resistor, do you have any voltage drop in different sections?
Do they differ in the different sectors? No, I don't believe so.
So you don't need to compensate that, or actually you need to compensate, but since you have a single high voltage channel, this can be done equally for all sections.
Yeah.
Right? Okay. And this was fast. The second one is about the gas. I mean, you use argon CO2 7030. I'm wondering what is the driving choice for this type of gas, because I mean, this kind of problem can be even mitigated by changing gas. I mean, LHCb we're using a completely different gas. I mean, completely different.
Right. So there's a couple reasons that made us choose that. Really, one of the most driving factors is previously, years and years ago, gem detectors would use argon CO2, either CF4 or SF6. But these are very strong greenhouse gases, and we are trying to phase completely away from that. And so just the argon CO2 is a much more eco-friendly gas. And the ratio that we use, the 70-30, it's just a good balance between the multiplication and spark quenching. Does that answer your question?
Yes, thank you.
Okay, we were perfectly in time. Thank you,
Yay.
Elizabeth. Thank you for your very nice talk. Let's move on to the next speaker. I will try to pronounce it well.
As soon as I figure out how to stop sharing.
Okay, you don't have to.
Chattopadhyay.
Thank you.
From Fermilab and Northern Illinois University. He will talk us about quantum sensor of the dark universe, exploiting the quantum entanglement in the laboratory for detection of exotic particle and fields.
Can you unshare, because I cannot share screen?
Yeah, I'm trying. I'm sorry. I'm kind of new to Zoom. I think I got it.
Yeah, you got it.
All right, thank you. Thank you. That's great. Okay, let me go. Can you see my screen?
No, I'm seeing you.
Okay, let me see share. Wait a second, why can't you see me? Why don't you see my screen? What do I do here? Let's see. I just tried it with you, right?
Yeah, we tried just before this.
You can see it.
No, I cannot see. I don't know if others can see it. If it is a problem of mine.
No, we don't see also.
Okay, so.
Okay, so what's going on here?
There is this share screen button on the bottom of the Zoom meeting window. And if you click it, then you can select your application or your desktop.
I'll say join the meeting. Hold on just a second. Okay, I think I got it.
Yeah. Now I see your screen. Yeah,
do you see it?
With the Zoom. There is the Zoom. Okay, no, yes, I can see it.
All right, thank you very much. Well, now I'm going to change gear to ordinary detectors to quantum sensors. I thank the organizers for giving me a chance to talk about this new topic. In 10-minute talk, I cannot really get into details, but I try to give you a flavor. Quickly discuss the role of sensors, classical and quantum. Talk a little bit about these sensors I'm going to talk about are not going to sit in the path of a beam, but they are going to just sit in space-time and probe the universe as it is. I'll give 3 examples of these: cavity qubit-based detection of dark particles, atomic interferometers to probe gravitational waves and dark energy, and designer materials, which are particularly good at diminishing the band gap between conduction band and valence band, so you could actually detect very weak particles. Sensors, of course, have been appreciated by people for a long time. Galileo Galilei told that you should measure what is measurable and make measurable what is not so. And the only way to measure things is sensors or instruments. You can see Humphrey Davy said that nothing tends to advance science as much as the application of a new instrument. And for us, this will be a new sensor. So conventional detectors, together with accelerators and theoretical understandings, have already given us a pretty close and complete picture of the standard model. However, there are a lot of unknowns still left, like the Higgs particle and the neutrinos, and maybe the dark matter particles, dark energy, and its connection to cosmology, gravitational waves, and so on. So my main point in this talk is that actually, at the very beginning, 13.8 billion years ago, very close to the Big Bang, entire universe was actually entangled, and you have evolved so far, but all the relics and fossils of that entangled universe is still there with us. And so rather than trying to create that energy in the laboratory, we should probably try to be archaeologists, a cosmic archaeologist, to look for the relics and fossils from the Big Bang. There's, of course, a mathematical description of entanglement. I'm not going to go into that. And so that becomes relevant. So when we talk about quantum sensors, what do we mean by it? It means by instruments that, of course, depend on quantum physics, like any ordinary detector does, semiconductor physics. But we are particularly talking about detectors that actually depend at a very fundamental level on the quantum entanglement part of natural systems. And these quantum entangled sensors have a higher level of precision to discovery class research. Why I'm saying that is that if you just simply look at two quantities, X and Y, that are independent, and you can only do so much in understanding each one of them and resolve each quantity to the best possible experimental resolution. But if you somehow entangle or correlate the two objects, and if you don't care about one of them, let us say X, you can squeeze it in the X direction so that you can actually get a much higher precision in the Y, and vice versa. And this actually is already, I can illustrate that by a simple example of simply measuring a radio signal or a microwave signal. And of course, that has an amplitude, intensity, and a phase component. And if you look at that signal, has a little footprint in the amplitude and phase diagram. And typically, it has a noise component, a thermal noise, depending on the temperature, kT, half kT, and a quantum noise component, which is at least one photon per resolved mode, and which you cannot. So depending on the temperature of the system, you can actually get to a certain floor level of noise. Now, if you make the amplitude and phase correlated by quantum non-demolition technique, you can, if you don't care about the phase, but simply want to know how many photons are there, or what the intensity or amplitude of the signal, you can smear out the phase in 2 pi and simply count the number of photons that you have without destroying the actual signal. And this actually can lead to many, many orders of magnitude improvement in signal to noise ratio. So here I give you one example of what one can do if you use this quantum non-demolition technique. If you take typical temperature, and you can, if this dashed line on this thing is a single quantum noise limit, standard quantum limit. At a high temperature, you are still dominated by quantum limit. As you lower down the temperature from room temperature to all the way down to 10 millikelvin, down here, this blue line, you see that you are not really dominated by the quantum noise anymore, but you are dominated by the thermal noise. So that means the noise will go down as you go down to absolute zero. So these techniques of quantum non-demolition technique and squeezed states can only work if your system is entangled at the very fundamental level. And I'll give you some examples of these later on, but just to tell you quickly that some of the areas where these applications are very useful are if you want to search for new particles or new interactions like dark matter or dark energy, or you want to probe the very early universe, inflationary cosmology. I will talk about these two quickly. Quantum computers, of course, everybody talks about. Big biosignals from very environmental signals, neuroscience. One can actually use strongly correlated special types of materials, like the Dirac and Weil materials, to detect very weak signals. And of course, one can detect very weak environmental signals for climate change. I'll give you now 3 examples in physics where quantum sensors are actually already being used. One is actually a qubit-based single microwave photon sensor for dark matter axion detection. Here you have a cavity, hopefully a superconducting cavity with a very high quality factor. Inside you embed a little Josephson junction or a qubit. And you use this quantum non-demolition technique, and you actually look for, if you embed the cavity inside a magnetic field, you can look for a photon at the frequency of the cavity appearing from nowhere when you do not have any such signal in the environment. If you can suppress the noise level of this cavity by quantum non-demolition technique to its lowest level, you begin to see a signal appearing at the frequency of the cavity, which must be either a new particle or a new wave going through the cavity. This actually is being funded right now by private in the foundations like Heising-Simmons and DOE Department of Energy Quantum Initiative. And we have an experiment at Fermilab that is being planned. And if you look at the experimental physical reach of this kind of a system, if you plot the coupling of dark matter or axions to the axion mass, you can see that you can actually cover a large footprint on this diagram between 10 microelectron volts to a milli-electron volt class of weak and light mass, extremely light mass dark matter candidates. These are called generation 3 axion dark matter search experiments. A second application I will give you is in the sense of detecting space-time distortions from the very early universe in terms of gravitational waves at the level of 10 to the minus 25, the relative strain of space-time, dl over L, at 1 hertz. So this is where you expect the primordial gravitational waves like the cosmic microwave background radiation, cosmic gravitational wave background radiation to come about. You can also use this technique to detect actually dark energy. And one of the quantum sensors we are proposing and beginning to work on is actually atomic beam. If you think of an atomic beam that you actually let it fall under gravity, as the atom falls, its quantum mechanical wave function as a phase given by the momentum k times z. And if the distance it falls is not actually exactly what you think it is, but has a metric fluctuations in it coming from background gravitational wave from Big Bang, then the phase of the atom would be fluctuating. And when you take an atomic interferometer at the bottom, the atomic matter fringes would have imprinted upon them the information of the metric fluctuations. So we have a proposal at Fermilab funded by Moore Foundation, Gordon and Betty Moore, the semiconductor people, and Department of Energy Quantum Initiative to actually have a 100-meter drop atomic experiment. It's a, I show you the Fermilab site. There's 100
Sorry, Zwapan, you have 2 minutes left.
Yeah. There's a 100-meter shaft. And in that shaft, we are planning to do this experiment of dropping an atom, a strontium atom, and try to see if you can see any interference of the atomic wave function generated by the gravitational wave. This is a collaboration of Stanford, Berkeley, Northern Illinois, Liverpool, Fermilab, Cambridge, and Northwestern University. There's a lot of systematic noise, environmental noise, seismic noise, Coriolis effect, gravity gradient noise being studied. So environmental systematics have to be eliminated. But if they can be, then we estimate that the sensitivity of this detector in the gravitational wave range could be, as I show here, is between a millihertz and a hertz. And this is where there's a gap between LIGO and LISA. LISA is the space-based European program. LIGO is the land-based laser program. We can fill the gap between these two sectors. Similarly, there's a sensitivity plot for dark energy and dark matter search. Finally, I would like to say two more things is that one thing that these quantum sensors can be used is using molecules or trapped ions or cold atoms or qubits inside a cavity or vacancies in nitrogen, vacancies in diamond crystals and so. But also one can design materials like Dirac materials or Weil materials. These are topological materials, but the band gap between the conduction band and valence band is almost zero. So any weakly interacting particle, like a dark matter or axion or what have you, can instantly convert an insulator into a conductor, and you can have a detector on very weak processes. So let me just close by saying that the prospects of these types of novel detectors, which does not require a particle beam, but actually sits in space-time and probes the cosmic background coming from the Big Bang in terms of dark matter, dark energy, gravitational waves, is very, very promising. We should probably benefit in the community from more investment into these types of research. And it is actually picking up in Europe and in America and in Asia. And we look forward to a growing development of quantum sensors in the future. Thank you.
Thank you, Swapan. Very nice talk. Question or comments for the speaker? I see that Paolo Yengo has raised his hand. I don't know if it is for the previous talk or for this one.
Yeah,
Paolo, do you have a question? I don't think so. Okay. So I don't see
your hand is raised.
Yeah. I saw that you showed that you built a detector formula for dark matter direct detection. Can you say more about the dimension, the mass, and do you think that this kind of sensor could be used for detection of heavy dark matter? Or only
No. These are very light dark matter, and the mass of the matter is tied to the frequency of the cavity, and the cavities are typically between 1 gigahertz to 20 gigahertz. So if you convert that frequency of 1 to 20 gigahertz to mass, they come to like milli electron volt to micro electron volt. So we are not talking about heavy dark matter at all. But and with the atomic drop experiment, if dark sector couples to the standard model world, you would expect that the alpha, which is fine structure constant, should fluctuate by the interaction with the dark sector. That means the atomic transitions would be affected by it. And we calculated to what degree we can actually look at coupling of atoms as a quantum system to dark sector. Again, the mass range that we are talking about there is very low mass, light dark sector, not
I understand. Yeah. That's very clear.
Yeah.
Thank you a lot. Thank you a lot. I don't see any other resident, so we can go to the next speaker. Sorry, who is Cedric Deos from HL-LHC for the WADAP consortium. We'll talk us about WADAP, the wireless allowing data and power transfer. I can see your slides.
Okay, can you hear me also?
Yes, please go.
Fine, okay. So good afternoon, everybody. Today I will present you some works done in the framework of the WADAP initiative. So WADAP means wireless allowing data and power transfer. So in this presentation, I will precise the context and motivation of the WADAP initiative before focusing on the wireless readout using a millimeter wave. I will show you some early feasibility tests for high energy physics application. And at the end, I will present you some conclusion and perspective around the wireless technologies. So the WADAP collaboration gather multiple research institutes and universities all around the world, as you can see on the map. The goal of this collaboration is to assess the wireless technologies for various high energy physics applications. So why using wireless? As you may know, the cable are quite awkward in experience. It creates multiple scattering and nuclear interactions and dead zone areas. And these cables can impact the way the installation is done and the operation. So moreover, the cables are always put in axial side, so it's an axial readout, and this installation can induce important latencies. So as an alternative, we are proposing to use wireless technologies in order to have a direct communication between layers. And so using RF ICs, we tend to minimize the material budget of cable and connectors. And by the way, we are limiting the radiation length of the services. So moreover, by using wireless technologies, we can have more flexible link placement into the experiment. And we can have point-to-point or also point-to-multi-point links. And we can also imagine having interlayer intelligence. So moreover, by using wireless, the data will follow the event topology, so enabling fast triggering. So however, this kind of, if you take the example of Atlas or CMS, there is a high demand of bandwidth, so data rates. So it's true for present and also for future experience. If you see the example of Atlas Phase 2, you can see that up to 10,000 links are expected operating at 5 gigabits per second. And these links are very close together. So it's a few centimeter range between the different links between the detector and the outer enclosure. So as an alternative, what has been proposed by Richard Brenner from Uppsala University is to use a wireless readout. So they expect to have RF IC close together to the detector, and the signal is transferred with multi-hop up to the outer enclosure. So each wireless link here is only a 10 centimeter range. And the difficulty here is to have high data rate links consuming low power with no latency, and also to have multiple links close together. So the difficulty is to manage the crosstalk between the links. So in order to answer this issue, we have proposed to use millimeter wave technologies. So millimeter wave means frequency between 30 and 300 gigahertz. So it corresponds to short wavelengths. So it can the antenna can be very small at those frequencies, and we can have a compact system on chip. So the antenna can be integrated into the chip or into the package. Moreover, at this frequency, we have a high free path loss, so the signal quickly vanished. So it's suitable for short range, and the good thing is that we can reuse quite easily the frequency. And so we can have multiple links close together. One important thing also at those frequencies that we can still use low-cost CMOS technologies. So we have demonstrated high data rate links in V bands, so around 60 gigahertz, but also in D bands around 140 gigahertz. So with a very high data rate. So there are two possible radio frequency architecture for this kind of short-range links. If you want to use phase and amplitude modulation, you will need to have a synchronization between the emitter and the receiver. So you will need a precise frequency synthesis and also a digital baseband circuit in order to achieve the synchronization. Another possibility is to, for amplitude modulation, so on-off keying, is to use a simple emitter with a free running oscillator. And at the receiver, we will have a simple envelope detector followed by a comparator. By using this kind of architecture, we can achieve a very low power, but poor spectral efficiency. So using this architecture, we have developed in collaboration with ST Microelectronics a CMOS transceiver, so in a CMOS 65 nanometer technology, using a non-coherent architecture. And the performance, so we can achieve a data rate up to 6 gigabit per second at a few centimeter range. And the power consumption is very low, around 35 milliwatt. So another chip is under development at Heidelberg University. So this chip is more dedicated to high energy physics application. Strong attention has been paid to robustness and reliability to HCP environment. So I would like now to show you some early feasibility tests. So the first one is about the signal integrity for high data rate transmission. So for this example, we have used both coherent and non-coherent RFIC. So it's commercial chips. And we have found that even up to a few gigabit per second, we have a good quality of service. So we have checked as the spectrum, the bit error rates, the eye diagram, and made also a jitter analysis. One important point is for the non-coherent RFIC, the latency is very low, so we have measured it below 1 nanosecond. At Heidelberg University, they have carried out feasibility study regarding the intra-layer signal confinement, so that they verify that the signal stay between two layers using SCT barrel module. So the module completely block the 60 gigahertz signal. They have also verified the coexistence with a few detectors. So they have found that no increase in the noise floor under 60 gigahertz emission. And they have also studied the crosstalk with the assumption of a 5 centimeter pitch between the different links. By using a directive antenna and polarization diversity, the isolation between the links stay always above 25 dB, which is enough for a good quality of service for the signal. In CELAT, we have also interfaced 60 gigahertz chip with 3 megapixel detector from IPHC Strasbourg, so without any issue. Using the chip is interfacing using standard SLVS, so there were no issue about that. And the last test was about irradiation. So it has been carried out by Uppsala and Heidelberg University using CMOS 65 nanometer transceiver.
You have 2 minutes left.
Okay, thanks. So this irradiation test has been carried out at Turku for proton beam irradiation with 19 megawatt energy dose. And we have measured the performance of the chip before, during, and after the irradiation. So we have found that a few rare errors have been detected during the irradiation, but after the irradiation, the transceiver completely recovered. And only a small alteration of the budget link has been measured, so around 3 dB. A neutron flux irradiation has also been carried out at CERN Clear with a 50 megahertz dose. This time, the band gap of the RFIC has been broken, so the voltage reference was not good enough to have a good performance, but the transceiver is still operating. So that's quite a good result, assuming that the CMOS transceiver is dedicated to the mass market application without any hardening. So now we'll pass to the perspectives. So for the short-range connectivity, in the next 2 years, we plan to have a protocol compliance into the RFIC chip, adding some digital part of the chip to be completely transparent to protocol. The chip will be also able to be compliant to full duplex operation. And in the next 5 years, we plan to have an increase in data rate, achieving 20 to 40 gigabit per second, so challenging the optical links. At medium range, we can use coherent architecture, and more particularly, we can imagine aggregating multiple channels in different frequency. So it's frequency division multiplex in order to gather all the data and send it with a very high data rate. We have started to work at D-band in HL-LHC, and the transceiver we have developed is achieve more than 100 gigabit per second today. So as a conclusion, millimeter wave allow high data rate, low power communication at short range. The non-coherent RFIC architecture can be used for low power and low latency, so at short range. Antenna scheme may add directivity gain to increase the range, but also to manage the crosstalk. Early feasibility studies show no deadlock for the use in high energy physics application. So commercial products are now available, so at 60 gigahertz, so you can play with it, and it can be customized for particle physics detector. And a dedicated chip is under development at Heidelberg University. So future development should challenge optical links at short range. And I would like to say also that there is a proof of concept of pixel detector readout under specification with the collaboration with HPHC Strasbourg. And also the power transmission and energy harvesting are also considered for a full contactless connectivity. If you have any question of the time.
Yes, we have time for one question. Thank you, Cedric, for the very, very nice talk. I don't see any raised hand. I have just one curiosity. Clearly, wireless transmission is something which is a dream for all experimental physicists. The problem is clearly related to the noise which this device can induce on the detector. I saw that you showed in one of your last slides that in Heidelberg they are managing to do something to limit the noise. Can you say something more?
Yes. Since we are the transmission is done at 60 gigahertz, so it's very high in frequency. So the impact of this millimeter wave on a PCB is very low. It's very difficult to have some interference coming from 60 gigs. And let's yeah. Because okay. all the clock in the detector, if you have clocks, they will operate far more below in frequency.
Yeah. Thank you, Cedric. I think if I don't see any other raised hand, we can interrupt this section here. We have 15 minutes coffee break, and we resume in 15 minutes.
Thank you.
Okay, bye-bye.
If there are any speakers who would like to test the share screening, screen sharing and microphone, now it's a good time.
Hello, can you hear me? This is
Yes,
Esteban.
I can hear you.
Okay, perfect. So microphone working, thank you.
Would like to try sharing screen or not? Not.
Yeah, I can try as well that. So do you see the slide?
Yes, I can see.
Okay, perfect. And stop sharing.
Anyone else?
Hello, can you hear me? This is Mu Wei.
Yes, yes.
Good, thank you.
Okay, we can restart this session. We have now a series of 3 dune-related presentations. We start with Guillaume Eurin from CSACLE, which will tell us about the proto-dune dual phase contraction and the first results. I can see your slide.
Okay, perfect. Can you hear me?
Yes, please go on.
Great, thank you very much. So it's a pleasure to be here today to talk to you about the proto-dune dual phase detector. So I will start by introducing quickly the deep underground neutrino experiment, which will be a long baseline neutrino oscillation experiment for which there are several primary physics goals, such as the measurement of the delta CP or the determination of the neutrino mass ordering. So the experiment will have a neutrino beam produced in Fermilab and detected in the far detector site, so 1,300 kilometers away here in the Sanford Underground Research Facility. There is a plan to have 4 17 kiloton liquid argon TPCs installed 1.5 kilometer underground. And there is already a liquid argon R&D program going on installed at the CERN neutrino platform, which are the so-called proto-dune dual phase and single phase detectors. So just to give you an idea, this is a picture here of the neutrino platform at CERN, where you can see here in the front the single phase detector, and here in the back you have the cryostat of the dual phase detector. So I will give you a few explanation about the operating principle of the proto-dune dual phase. So it's a liquid argon TPC that is filled with 720 ton of liquid argon and for 300 ton of fiducial. So when a muon, for example, crosses the fiducial volume, there will be ionization and scintillation produced. The scintillation will be detected at the bottom of the detector by our photomultiplier tubes, and the electrons will be drifted in a drift field towards the gas liquid interface, where it will be extracted from the liquid into the gas by an extraction field into the large electron multiplier, where the signal will actually be amplified and then finally detected at the top of the detector and on our anodes. So thanks to the principle of the dual phase TPC, we have a 3D track reconstruction, of course. So a few more words about the principle. So as I said, we have a drift here. This drift field is of roughly 0.5 kilovolt per centimeter in the baseline over 6 meters. Then we have this extraction grid here, and between the bottom face of the large electron multipliers and the extraction grid, we have 1 centimeter across which we have the extraction field that is applied of roughly 2.5 kilovolt per centimeter. Then inside the lamp, so you can see here a picture of this 50 by 50 square centimeter lamps, and here in a bit more details in the zoom of the holes that are actually in the detectors is where the charge signal will be amplified, and we have an amplification that is on the baseline as well, around 20. And then finally, we have a 2 millimeter gap before reaching the anode. So you can here again see the picture of the anode with the strips. And we have actually a 2-view collection principle where we can see in X and Y, basically the signal that is deposited with a precision of 3 millimeter pitch. So it's of course a challenge to operate such a big detector and actually to instrument across this very small 1 centimeter gap the detector, and also to keep this liquid level exactly where it should be. So to give you an idea, here's a picture from the inside of the cryostat. So you can see here the field cage, and here at the bottom we have the cathode. Beneath the cathode we have the photomultiplier tube that you can see here as well on the sketch. At the top you have the charge without planes, and in these planes are actually where the extraction grids, the large electron multipliers, and the anodes are installed. So to give you a quick idea, the main detector was installed in March of last year, and the cryostat was closed in May, and the manhole, so the final seal, was done in June. A few words about the commissioning. So here you can see again in the neutrino platform the hole where the cryostat is now installed. So the construction of the cryostat started in March of 2017. The detector was installed started actually in 2018, and then it took roughly a month to close the cryostat, then purge it, and start the cooling down. Again, for roughly a month, we had the liquid argon filling, so between July and August of last year, and by the end of August last year, we had the first tracks measured with cosmic rays. So a few more details about the charge without planes. So you see here we have 4 of these charge without planes. 2 of them are equipped with each 36 lamps. And what you see here from the side is, again, the anode with the 2 millimeter gap with the lamp here, and then the 1 centimeter gap with the extraction grid. So it's critical due to the 1 centimeter gap that we have to have the best planarity possible for the CRPs. And the planarity was actually measured to be plus minus 2 millimeters. And there's already some improvement for the second phase of the experiment that are already made in order to improve this number. I also said that it's important to keep the liquid level exactly where it should be. And for that, we have an automatic tracking of the liquid level. So as you see here, for example, in the level meters, the level was rising and there was an automatic correction by the system that is actually actuated there. And we have a precision for that of roughly 100 micron. One of the key aspects of the dual phase TPC here is that the front-end cryo amplifiers are actually remaining accessible during the entire operation. That means that if something gets damaged, we actually have access to it and can do some repair and do some exchanges. This is achieved through these chimneys here, which are 2 meter long, in which we have these so-called blades, at the bottom of which we have the cold front-end analog electronics, which are installed there. And actually, afterwards, the signal is guided to the top of the cryostat, where you see here the top of the chimney, and then read by the digital front-end electronics. And we have a total of roughly 7,000 channels read out here by our electronics. All right, so as I said, we also have measure scintillation in our detector, and this is done by the photo detection system. So we have 38-inch cryogenic PMTs from Hamamatsu, which are using 2 different wavelength shifters. And they have been in operation since June of last year, and the position here at the bottom below the cathode was optimized by simulations for the light collection in cosmic ray events. And there is an embedded light calibration system for these PMTs, and the signal to noise is better than 11 with a gain of 10 to the 7, which actually is better than the requirement that was actually of 5. So there are several analyses going on for the performances and the physics done with this photo detection system. Here, to give you an idea, you can see the S1 signal, which is the primary scintillation, followed directly by the electroluminescence, the S2 signal, and this is here in the case of a track that is crossing the liquid level. Okay, so one of the main aspects of the operation of a dual phase TPC are the cryogenic conditions and also the argon purity. So as you can see here from a picture of inside our cryostat, we actually have, unfortunately, some ripples at the surface of the liquid argon, and also we have some bubbles that displayed here. So for the bubbles, we actually know where they're coming from, but we don't understand their origin yet. So we are working on this. But fortunately, as you can see on this picture, we have means to actually mitigate this liquid surface instabilities. Actually, what you see here are not waves, but the field cage that you see by transparency. And as you can see here as well, we don't have bubbles anymore. And this actually has been achieved using high pressure cycles. So the argon purity is, of course, also critical to be measured. So here we have the results of the 3 purity monitors that we have installed in the dual phase detector, and also the result from the dedicated analysis using the attenuation of the neon tracks inside our detector. As you can see here, we have a good agreement between this analysis and the short purity monitors. And we also reached the target of 3 milliseconds that was necessary for the electron lifetime. As you can see here as well, we have some dips at the beginning of the operation. This comes from the fact that we had the filter that are used for the liquid argon recirculation had some clogging issues, which fortunately improved from November on. All right, so we had an unfortunate incident at the beginning of operation, so in August of last year, where a short developed between the field cage that you can see here and the high voltage extender, which brings the 300 kilovolt in theory to the bottom of to the cathode. And in this connection here, actually the short developed. And this is here the consequence where you can see the position of the short on this COMSOL simulation, where you see that the electric field is actually very inhomogeneous. So this has an impact on the TPC performances. And but fortunately, this high voltage extender could be repaired last month by removing 1.5 meter of liquid argon, which corresponds to roughly 150 ton. And this faulty connection was cut, and the other 2 below for safety. And data taking is supposed to restart next month in order to take data with this homogeneous field. Another difficulty in the operation of the prototype dual phase detector is the sparking, and actually it is a source of improvement already for the second phase of the detector. So we have 2 systems that actually spark in our detector: the extraction grids and the lamps. The extraction grid are actually operated at 6 kilovolt high voltage, which means that when they are sparking, unfortunately, they cause damage to our front-end electronics, and this is what you can see here, where some channels actually become noisy. The origin of this sparking is unclear because the grid wires are supposed to be immersed constantly by at least 4 to 5 millimeter in liquid argon. And we also did some extensive high voltage stability tests to find the best operation for the detector. But the solution that we're going to go for the phase 2 is actually the redesign of the anode, and where we are going to add a guard ring at ground in order to protect the front-end electronics. So as I said, the LEM are also sparking. We had a sparking rate target of 1 spark per CRP, so per 36 LEM, per hour. This was unfortunately not yet achieved, and for that we also have a redesign going on from the lamps in order to reduce this sparking. And for example, as you can see here, we have some insulator that is added at the fixation holes that we need for the lamp anode sandwich, and also on the edge here of the lamp. There's also new technology that are being investigated for these lamps, such as the use of segmented lamps or the addition of a resistive layer. Okay, in spite of these issues, we have been able to acquire some very nice data. So as you can see here, some event displays from our detector. So for example, you can see here we have a horizontal muon track, some electromagnetic shower and muon decays, also some multiple hadronic interaction in the shower. And something that is very interesting to see as well is the noise level that we have, which is at roughly 1.
William,
yes,
you have 2 minutes left.
Yes, thank you. Where we have roughly 1.5 ADC, which is very low for our detector. So before coming to my conclusion, I want to show you a main measurement that we have been doing with our detector, which is the charge without plane gain. So when I'm talking here about CRP gain, I'm going to talk about the combination of extraction, amplification, and collection. This CRP gain, as you can see here on this plot, is plotted as a function of the high voltage across the lamps. And here we have the intake data between September of last year and January this year. What we have here are the data sets from September and October, and here the data set from November and January. What you can see is that there is a drop of roughly a factor of 2 of this CRP gain between September and November. This actually is something that we expect from the lamp charging up effect due to the design of the lamps. What we can see afterwards as well is that between November and January, so between these two sets of data, there's almost no reduction anymore, which means that the charging up was actually completed. Unfortunately, what you can see here in black is the gain that was extrapolated from the previous prototypes, where we should have had actually our gain after charging up, and unfortunately we have a factor of 2 that is lower. So the discrepancy is not yet understood, but there is a dedicated study that actually is to come with the next data. So that brings me to my conclusion. So pollutant dual phase is already a proof of principle that has been achieved for the operation of a 720-ton dual phase equilagon TPC over 4 CRP units of 3.3 by 3 square meter. We had an unfortunate short on the high voltage extender, but this has been fixed now. The CRP gains are lower than expected, and this is something that we need to understand. We also have an R&D campaign going on for the lamps that will go on until 2022 for the second phase of the prototype dual phase detector, and also other part of the CRPs will be upgraded, such as the anode, the grid fixation, and the planarity. We still need also to understand the origin of the liquid-argon surface instabilities, but hopefully with this foreseen improvements, we should be able to demonstrate the feasibility of a 17 kiloton dual phase module for the fire detector. Thank you.
Thank you, William, for a very, very clear talk. Other questions or comments? I see Andrew White, please.
Yeah, hi. Do you have environmental transient concerns, for the creation of the surface liquid argon?
I'm sorry, you're breaking up. Can you repeat your question?
Yeah, I just wondered if there are environmental sources of transients that could cause variations in the liquid argon level.
So we have actually observed a very, very constant liquid level. Actually, we had overall from August last year until the end of the operation in May mid this year, we only had a reduction of 4 millimeters, but there was no really day-night oscillation that we could see, for example, or something like this. The liquid level remained really stable over time.
Yeah, I just wondered about the final location of the detectors, whether there would be environmental effects there.
So I don't think so. To my knowledge, there was no impact from environment on the liquid level. The insulation of the cryostat was efficient enough to actually prevent any impact from the outside.
Okay, thank you.
Sure.
We have time for one more question. I have one. Sure. Did you have the chance with this repair that you did to investigate the source of the bubbles?
So actually, so the source, let's say the location of the bubble is actually understood. So our field cage is made of this aluminum profile that you can see here, and we have clips in between. So we know that this is the location where these bubbles are forming, and actually afterwards being liberated from there when enough gas is produced. The thing that we do not understand is the mechanism that is creating these bubbles. So this is something that is gas in the field cage. So that's something that we actually are going to try to investigate. But even during the operation here, this this repair, we only removed 1.5 meter of argon. We didn't empty completely the cryostat, so we could not get inside. The repair was done by inserting tools on 3 meter long pole from the top of the cryostat and coming and cutting the pieces here that we wanted to remove and then taking the backup. But this is something that will be investigated at the end of the operation of the first phase for the hopefully fixing it for the second phase.
Okay, thank you. Thank you.
Sure.
I don't see any other hand raised, so we can move to the next talk from Victor Peck from the University of Sheffield. We'll talk us about the calibration of calibrating the Dune liquid argon TPC detector for precision physics. Please, Victor, share your screen. I can see your slides. I'm not hearing you.
Right, do you hear me?
Yes, please go on.
Very good. All right, great. Thanks for the introduction. Hello, everyone. I'll be talking about our plans for calibrating the Dune liquid argon TPC detectors. So you've already heard about Dune, so let me just quickly remind you that Dune is a neutrino oscillation experiment which consists of a far detector and near detector at Fermilab. The oscillation happened at a baseline of 1300 kilometers, and the far detector consists of 4 17 kiloton modules. The near detector also has a component of liquid argon TPC, and liquid argon TPC is what I'm gonna talk about. The calibration or the detector performance drivers for our calibration efforts are mainly from our broad physics spectrum, and the main drivers being the measurements of CP violation and neutrino mass ordering, that is for energies at GeV scale. And also the second significant driver for the performance are detection of neutrinos from supernova bursts, which are at the order of MeV scale. We are also considering requirements from other physics, like baryon number violation and atmospheric neutrinos and so on. Now moving on to liquid argon TPC. So the principle was already described. Basically, you have a charged particle passing through active volume, which creates charge, which is being drifted by electric field, in our case 500 volts per centimeter. And the drifted charge is then collected at the anode plane, and combining the drift time and location on the anode plane, you can do 3D reconstruction of the deposition itself. On the bottom left-hand side, there's an example of event display from ProtoDune, where you can see a pion and interacting within the detector. The major effects which we need to consider when calibrating our detectors are recombination, where the electrons immediately after being produced by the ionizing particles can recombine before being drifted away. We also need to measure the drift velocity or determine properly electric field within our detector, which will be essential for measuring the drift coordinate. And also we need to measure electron lifetime, where we will be losing electrons, drifting electrons on their way towards the anode due to the attachment to the impurities. There are other effects which we need to also measure, and those are electron diffusion and electronics gain. The strategy we developed to achieve our goals is first to establish connection between the physics measurement sensitivities and our calibration requirements. And then we need to develop procedures to determine the fundamental detector parameters, as you just saw on the previous slide. And then measure the detector. We want to measure the detector response to so-called standard candles, which would be, for example, through-going muons and stopping muons, Michel electrons produced by decay of those muons. We can use delta ray electrons, pi node decays and neutron capture and natural radioactivity. Now, for the sources we can use for the calibrations, we can make use of multiple of those. So we will have interaction from cosmic muons inside the detector, also interaction from beam and atmospheric neutrinos, and we have some intrinsic radioactive isotopes inside liquid argon. We are also designing dedicated calibration devices, such as ionization laser system and pulsed a neutron source. We are also considering a dedicated gamma source. Now moving to cosmic muons. So we will be having about less than 5,000 of muons at a single detector module at far detector per day. On the right-hand side, you can see this expected spectrum of these muons with mean energy of about 280 gigaelectron volts. Out of these 5,000 muons, only about 90 will be stopping inside the TPC. So I already said that we can make use of these cosmic muons for various use cases. So they're a rich source where we can use them to measure electron lifetime, the electron recombination. We can do alignment. We can also measure or use the standard candles like delta rays, Michel electrons, and measurements of minimum ionizing particle and Bragg peak of stopping muons. On the bottom right-hand side, there's an example of the effect of electron lifetime on the measured depositions by cosmic muons, and where you can see the readout charge per unit length versus the position in drift coordinate. And you can see that the readout charge basically is dropping as you go far away from the anodes. Another intrinsic source we will be using is the argon-39. This is naturally present isotope, and we will be having about 1 becquerel per kilogram in our detector. Argon-39 will beta decay with Q value over half MeV, and will have a very well-defined spectrum. Therefore, we can use it as a standard candle. On the right-hand side, there's a microbel measurement, where for 2 different thresholds, they were demonstrating that they could measure well the beta spectrum. The advantage of this source is that we will have high statistics of it, and it is uniformly distributed within our detector. And the spectrum itself is sensitive to electron lifetime, recombination, and electronics noise. The challenges will be that these are only for low energy region, and we will not know the position in drift direction due to the those decays happening randomly in time, and due to the large amount of those and low energy, there are also some difficulties in order to figure out how to do triggering and data acquisition. We are also considering a use of argon-42, which is another isotope which will be present in our detector. And now moving on to pi nodes. Pi nodes are good because they are decaying into 2 gammas, and we can use the invariant mass of the 2 gammas as a standard candle. Here on the top left is an example of a microboon event display, where this is an interaction of charge current interaction of neutrino. So detectors, you can see 2 proton tracks, 1 muon track, and candidate showers from the pi node decay. On the right-hand side, the microboon also show that they can measure the reconstructed invariant mass of 2 gammas, which is peaked at the mass of pi node, and they demonstrated that they can do good matching between data and Monte Carlo simulations. The advantages of this source is that we will have pi nodes from beam neutrino interactions and also from cosmic muon interactions. We can use them to probe the electromagnetic energy scale for these showers at this energy scale. The challenges are that it is very difficult to select do proper selection of these two photons, especially for cosmic muon interactions where we are expecting quite messy environment from other products. And we will probably have very low statistics as well. Now to the dedicated systems. So we are designing an ionization laser system. This was already used in Microboon, where they were leading their laser beam into their cryostat, and using steerable mirror, they could illuminate a large fraction of their active volume. This is on the bottom, there's an example of how they use the knowledge of, exact knowledge of their laser tracks to map out the distortions in electric field. So you can see the map in X and Y direction of the distortions of electric field in the drift direction. On the right-hand side, I show a schematic of our designed periscope that will be retractable and having steerable mirror. And this is the interface which brings the laser beam inside. And we are currently considering multiple
Victor, you have 2 minutes left.
Thank you. We are considering multiple periscopes and also considering using aperture in the field cage so that we can increase the coverage of the active volume. This laser system will be tested in Protodune Run 2 end of the next year. The advantages of the system is that it will provide high statistic measurements, will give us it will give us a possibility to measure electric field, do alignment, and possibly lifetime measurement. The challenge may be that the coverage will be limited depending on the design we decide on. Another dedicated source is the pulse neutron source, and this will make use of the existence of anti-resonance in neutron elastic scattering and liquid argon, which renders the liquid argon relatively transparent to these neutrons, and they can travel far. Neutron captures will produce gamma photons cascade of 6 MeV. There are now ongoing measurements at Los Alamos, namely ACE experiment, which will measure the gamma spectrum from these neutron captures, and RT, which is measuring the elastic scattering and the advantages of this system is that it is triggered and it has will provide high statistics. We can measure the response to neutron capture and determine the gamma energy scale, and also possibly measure the electron lifetime. The disadvantage is that we will likely have highly non-uniform coverage, and we'll have difficulties with associating scintillation light with individual interactions. To finalize this talk, I'll need to mention that there's a rich program of liquid argon TPCs going on now. So we have prototype detectors at CERN, which you already heard about. We are testing the single and dual phase technologies. They are already informing our calibration our development of calibration strategies for Dune far detector, and they are kind of measuring already the liquid argon properties at the same electric field, which is important, and the same drift distance as will be in our Dune far detector. There is a space charge buildup due to the fact that these prototypes are at surface, so there's a high rate of cosmic muons, but this is not expected to be a problem in near detector and far detector. And also, Protodune single phase already has been calibrating these effects out successfully. There's also Dune will also benefit from the rich short baseline neutrino program at Fermila, which employs.
Victor, you should try to wrap up your talk.
Yeah, sure. So. Which will use the liquid argon TPCs too. So, and just to summarize that, these are the drivers for our performance are the neutrino oscillations and low energy astrophysical neutrino physics. I have outlined a strategy to develop calibration techniques And we'll be combining intrinsic sources and dedicated devices. And also, again, Dune will benefit from the robust liquid argon TPC calibration program. Thank you.
Thank you, Victor. Very nice talk. Are there questions? If one, please raise your hand. You have time probably for one question. Don't see raised hand. I have a fast question. Sure. Can you tell us which one of the calibration techniques you have spoken about will be tested in ProtoDune in the next run of ProtoDune? Will all of them be tested or not?
Right. So basically most of the intrinsic sources are being tested right now because ProtoDune has been running, and right now at the moment I know that the laser system will be tested, and I believe there's also consideration people considering the test of the pulse neutron source tested as well.
Okay. Thank you. I don't see other residents, so thank you again. So we can move to the next next speaker, which we move from Fermilab. Will tell us about the photon detection system of the single-phase Dune-5 detector. Please, you can share your screen. Okay, I see your slides.
Good.
I can hear you, so please go on.
Okay, thank you. Thank you, everyone. Welcome to my talk on photon detection system of single-phase Dune-5 detector. As you already know, Dune is an experiment for neutrino physics and proton decay studies. Here, I would like to emphasize that Dune will explore several fundamental questions about the nature of matter and the evolution of the universe, such as the origin of matter via neutrino oscillation measurement, the unification of force through search for proton decay, and the black hole formation by observation of supernova neutrino bursts. Here, as we know, in a TPC, a charged particle will excite and ionize the argon atoms, and the ionized electron can drift towards the anode over the course of a few milliseconds and finally be read out by wires. Then from the charge signal, the track and the energy of the particle will be extracted. However, as we can see, only a part of the deposited energy will produce drifting electrons. The remaining energy goes into the scintillation light, and the light signal can provide additional information for particles. Compared to ionized electrons, the scintillation photons are much faster. They can be detected in nanoseconds after production. Therefore, the scintillation light provides a clock start time, or the so-called T0 for each event. T0 here is not so crucial for neutrino oscillation measurement. However, it is not the case for proton decay. We need to measure the T0 to know the vertex of the event. It allows us to visualize the event and reject cosmic background. Also, T0 will also help to reconstruct proper location and provide a complement trigger scheme for supernova neutrinos. Photon detection can also measure calorimetric energy. This energy can work as a cross-check of the energy measured by the TPC and improve the energy resolution. In the meantime, in case that TPC cannot operate at its desired electric field, the calorimetric energy measurement could compensate for the reduced charge, because as you see, the anti-correlation between light and charge. And the photon detection could also open new areas of investigation. For example, the few MeV scale solar neutrino interactions occur at isolated events in time and space. Surprising background requires redundant measurement with charge and light. The light may also provide a method for identifying events with Michel electrons. Taking this kind of electrons can be used to estimate the anti-neutrino content of the beam flux or further reduce nuclear decay background. Today, I will introduce the photon detection system of the single-phase Dune-5 detector. The single-phase dion detector is a 10 kiloton liquid argon TBC. It reads out the pattern of ionization with sub-centimeter granularity, and it is designed to search for MEV to GeV skew neutrino interactions. The principle can be illustrated in the figure on the right. Considering the design of the TBC, the photon detection module is designed to maximize the active volume of the detector and maximize the light yield. Due to the constraint of the core component of the detector, the anode plate assembly structure, or the so-called EPA, the photon detection module should be compact. Therefore, 16 PMs are selected as the photon sensor. In order now to impact on the detector active volume, the photon detection module is designed to be able to place in the inactive space on the APAs. You can see the figure on the bottom right. Another issue we should concern is that although the cost of silicon PMs has dropped in recent years, covering such a huge detector would be very expensive. Therefore, a large area light collector solution is designed. Now, let's review the baseline design of the photon detection system. I would like to divide it into 3 parts. First, the light collector, and then photon sensors, and then the electronics. The light collector on the left is used to collect UV light, convert them to visible photons, and then guide the photons to the sensors. So it is required to have large area and high photon collection efficiency to make sure that as many photons as possible can reach the photon sensors. Although full validation of the light collection system is still in progress, the so-called XL-LHC prototype is very promising. I will introduce you later. In the middle, we can see the silicon PM array. In fact, 2 silicon PM modules have been investigated as a photon sensor. The photon sensor is used to convert the photon to electrical charge. Certainly, the higher the photon detection efficiency is, the better. Also, the sensor will be working at cryogenic environment for a long time. Then, the reliability of the mechanical or electronic performance of sensors are at cryogenic temperature is essential. And at the same time, to reduce the readout channel, we will sum the sensors. Therefore, the terminal capacitance of the sensor is also an important factor. The electronic include the cold and warm electronics. It's used to collect and process electrical signals, provide the interface to trigger and timing system, and then enable data transfer to an offline storage system for further analysis. So it needs to measure T0 accurately, and it will be better to be cost effective. However, the core component of the photon detection system is the light collector. I will show the XL-LHC prototype. LHC in principle is a photon trap. What Dion plan to use is the second version, or the so-called XL-LHC. The idea is to trap photon inside the box with highly reflective internal surfaces, so that the detection efficiency of trapped photon is high, even with a limited active coverage of its internal surface. The basic unit of XL-LHC is the so-called cell. As shown on the right, it consists of the PTP wavelength shifter. It shifts photon wavelengths from 127 nanometer to 350 nanometer. And then the dichroic filter. It allows the photon with 350 nanometer wavelengths to pass through and reflect photons with more than 400 nanometer wavelengths. And at the center of the cell is a wavelength shifter plate. It emits 430 nanometer wavelength photons. This photon will be trapped within the cell and guided to the photon sensors. 6 cells form a so-called supercell, as indicated in the button. Then 4 supercells make up a bar-like photon detection module. In total, for the single-phase Dion detector, 1,500 such kind of module will be used. The performance of the XL-LHC cell has been validated with alpha source, and we compare the result to the simulation as shown on the right. We got a global photon collection efficiency as high as 3%. This is much higher than the required collection efficiency, which is 2.6%. Regarding the photon sensors, CPMs from Hamamatsu and FBK have been studied. And finally, the module S13360 is selected as the baseline choice. And in the design, 6 CPMs are mounted on the so-called PMB, the photon sensor mounting board, and they are passively gowned as a group. 8 groups of signals are actively gowned and form a supercell. The figure on the right shows the gowning and the PMB. Then one photon detection module will contain 192 CPMs and 4 electronic readout channels. In total, for the detector, 288,000 CPMs will be used. It's a large amount. Then the electronic is very important for the system. It converts the electrical signal from CPM to data, and the figure on the right shows the signal path for photon detection system. The electronic includes the cold part within the TPC and the warm part outside the TPC. Within the TPC, all the electronics works at liquid argon temperature and is used to sum the signal from the 2,088,000 CPMs. Outside the TPC, there is warm electronics. It is similar to other big experiments. For DUME, the baseline choice references the system developed for the mu2E experiment readout system. Compared with other solutions, it is more cost-effective. Also, calibration and monitoring.
Sorry, wait, you have 2 minutes left.
Okay. It's very essential for any detectors. Considering the DUME 5 detector will be operated on the ground, the cosmic muon rate will be low and insufficient to calibrate or monitor the system response. Therefore, DUME will use a pulsed UV light source as the primary calibration and monitor system. The system consists of a light calibration module, which is placed outside the core state, and the quartz fiber cable and optical feed-through, and in total 45 light diffusers mounted on the cathode plate. In the figure on the right, the light diffuser used in prototype single-phase detector are shown as a sample. There are several projects that tested the performance of different components of the photon detection system. For example, the prototype single-phase project, it tested 3 different prototypes of light collectors and evaluated their performance. I noticed that in the morning, dentist talk shows the details. Another project is the iceberg test lab. It tested 2 different types of error poker and compared the performance of different warm electronics modules. In the near future, the SBND and the prototype single phase 2 will further test the photon detection system. Now, let's come to the summary. The photon detection system is very important to DUME physics goals. The baseline design system meets the experiment requirement, and more testing and validation of component design is on the way. So in one word, the performance of the photon detection system has been improved. Okay, that's all. Thank you.
Thank you, Wei. Are there questions or comments? Please raise your hand if you want to ask question to Wei. Let's see, raise your hand. I will make can you comment? You said that the photon detection system can improve the resolution of the detector for low energy event. Can you comment a bit on this and how much it can contribute to this improvement in the resolution?
In fact, if we see this figure, we see that 40% of energy goes to the charge and another 50% goes to the photons. The photon detection efficiency is not so high, but if we can reconstruct the some calorimetric energy from the photon, and then we, based on the current performance, the energy resolution can be comparable to the energy reconstructed by the TVC. So combine these two energy, we can improve the resolution, energy resolution.
Thank you. There are more questions or comments? Way. I don't see raised hands, so we can move to the next speaker. Thank you again. Next speaker will be Esteban Curas Rivera. Yes, from CERN. Will talk us about strategic R&D program on technology for future experiments. I can see your slide and
okay,
I can hear you. Please go.
So good afternoon. I'm going to present the strategy R&D program on technologies for future experiments on behalf of the EP R&D program. So this is the outlook of my talk. I'm going to start with the introduction to the R&D program. Then I'm going to talk about the implementation and work program. Then I'm going to review some of the activities ongoing now in the R&D program, and then the summary. We have a web page that you can visit under this link, but it's still under development. The motivation for the program is the following: that we know that many important developments at CERN and facilities that are being used now, they were initiated or at least significantly boosted more than 10 years ago during the white paper R&D program that was an R&D program that lasted for 4 years. As an example, we have the Red Hat DC-DC converters, the ASIC in 130 nanometers technology, and the GIF++ facility, for example. Then, taking into consideration that these development cycles are long, like 10 years, the R&D for the LHC phase 2 comes to an end around 2020, and we know as well the R&D requires expertise, experience, infrastructure, and continuity. So if we take these 3 points into consideration, we think that now is the right moment to launch a new R&D program. We should take into account as well that the next generation of accelerators and experiments are still very far in the future. So that's why we decided to just to go for a strategic technological R&D program and not focus on any specific experiment. Anyway, its results shall enable future projects to develop and build optimal detectors. And we will use as guidelines, for example, the high-lumi LHC and some studies like the FCC lepton and hadron collider. The main challenges that we have for the future detectors, it depends a bit of, we are talking about lepton or hadron colliders. So for the lepton, we require a very high vertexing precision, a few micrometers. So for this, we need to have very low material budget in these detectors. And we want to use as well calorimetry with adequate segmentation for particle flow. On the other hand, for the hadron colliders, we will need to cope with radiation hardness, heat rates, and pile-up, and data rates that are or will be like a factor of 10 with respect to the actual high-lumi LHC. As well, we will need, in order to handle this thing, time capability below 10 picoseconds and large and strong magnets. In parallel with this, we should do R&D as well in the common technologies like ASICs, links, software, mechanics, and detector cooling. Like our resources are limited, we need to make selections and priorities, and we are going to focus in these 3 points where CERN has already significant expertise and infrastructure, where CERN plays a leading role, and as well in the area which will be a key for the success of the future projects. The implementation and work program, everything started 3 years ago with a kickoff meeting in 2017. Then we had 2 workshops in 2018, and the plan and budget was presented by the end of 2018. The medium-term program of 2019 was presented, and a budget line for this R&D program from 2020 to 2024 was approved with 25 million Swiss francs, that it was around 60% of request. So because of this reduction, we needed to adjust a bit the plan, and it was presented in October 2019, and by now we are already ready to go. The R&D program is organized like I show here. We have a steering committee that is chaired by the department head, Manfred. We have a program coordinator that is Christian Johan. And we divided the program in 11 work packages. Each work package has the work package leader, the deputy, and an individual budget. All the work is carried out by fellows and students, and they are always supervised by a staff member of CERN. And there is no any specific R&D group at CERN. In this slide, I just show the different work packages that we have. The largest one is the work package 1, that is the silicon sensors, and this one is divided in 4 different work packages. And then we have gas detectors, calorimetry and light-based, mechanics, IC technologies, high-speed links, software, and experimental magnets. The red light means that some activities are on hold because of this reduction of the budget, but they will be initialized a bit later once we can find additional resources. And some of other activities, they will have work in parallel with the AIDA. Now moving on to the review of the activities that we are doing now in this program. I'm going to focus only on the work package 1, that is the silicon sensors, because mainly I'm involved in this work package. So as I said, it's divided in 4 different sub-work packages. We have the hybrid detectors, the monolithic pixel sensors, silicon modules, and simulation and characterization. And this last is where I'm involved. So going to the hybrid and hybrid sensors, the goal here is to target demanding applications that requires specialized sensors or complex ASICs features, like for example for the LHCb Velo experiment for LHC4. And in particular here, they need to handle very high fluencies, high hit rates, and high output bandwidth. They have to do R&D in detectors. They need to achieve a low time resolution below 50 picoseconds, and as well they need to work to achieve a very good spatial resolution. As well, they need to work in the interconnections. That this is a link to the work package 1.3 and with the ICHEPs. And the development of the ICHEPs is going to come a bit later. Several types of sensors will be studied, like planar, 3D, and LGATs that are especially interesting for timing. And activities are already started, like building like a beta setup for timing and doing some simulations in Garfield++ to study the signal generation. If we go to another work package, the monolithic pixel sensors, here the activities are divided into phases. The first one that will last between 1 to 2 years is just an initial technology selection and validation, and then an asynchronous architecture study in 180 nanometers. Then the phase 2 is going to run in parallel with 2 activities. The first one is the pre-prototyping of large, low power and high resolution sensors, especially for ALICE. And then the prototyping of fast and hard sensors. And this is for high lumi general purpose experiments. And as well in this phase, there will be a continuation with the first phase, that is the technology monitoring and survey training, design, and measurement framework. And here I just put some examples of transistor test structures and simulations of fast analog buffer and TCAD simulations on the charge collection. And then another work package, silicon modules. Here the activity is focused on the study and development of new modules for hybrid and CMOS pixel detectors, and study integrated modules assembly techniques for large area CMOS modules and compact hybrid modules. So the activities are focused in these interconnection techniques, like for example, here we have the chip-to-chip data transfer via wire bond. And we have as well here another example that are the copper pillars on the Malta chip. Then they study as well the post-processing on and dicing and thinning. Like one example is the laser dicing of CMOS sensors that you can see here in this picture, just to reduce the insensitive edge regions. Then go to the last
Mr.
work
I'm sorry,
package.
you have 2 minutes left.
Okay, thank you. Going to the last work package. In this, the goal is just to understand and optimize the performance of particle detectors. And as an example, we work with low gain avalanche detectors. We do studies on the timing performance of thin low gain avalanche detectors after proton irradiation. We evaluate as well the gain degradation with infrared laser. And we study as I said, the timing capabilities and their operation stability based on the noise level. Here, one example that after irradiation, the 10 to the 14, we can achieve with these detectors nice time resolution. But then if we keep increasing the bias voltage, we see that some popcorn noise appears and degrade the signal. This needs to be better understood. Then another project is the acceptor removal and defect characterization. The acceptor removal is the radiation-induced deactivation of acceptors that in p-type doping is in the boron. This has impact on the change of silicon conductivity, charge change of the sensor depletion voltage, and active volume. As well, in the LGATs, we see the loss of gain that this will have implication in the timing performance. And going to the microscopic origin, so we know that before irradiation, we have the boron that acts as an acceptor, like a shadow dopant. And after radiation, it combines with other elements and become a donor. And this can be studied with this technique that is the thermal stimulation current. And we can study the different defects and the concentration of all of them. And then the last thing that I want to present is a new setup that we are developing at CERN. That is the TPA-TCT setup, 2-photon absorption. That basically the difference between the standard single photon absorption and the 2-photon absorption is that with the single photon absorption, the energy deposition is along the beam, but with the 2-photon absorption, we have and the energy deposition only on the focal point. And this focal point is, we see here, only 1 micron by 10 microns, so very focused. And this will allow us to do like 3D mapping of the sensors. Like here we have an example, like some features that we can see on the of a HCV MOS, the deep and well, that cannot be resolved with a single photon absorption. And then going already to the summary. So we can say that after 2 years of preparation, we have launched an R&D program on detector technologies. This effort is very much into the tradition of the white paper and the program that was crucial for the LHC phase 1 and phase 2 upgrades. Many teams from CERN and many teams from the CERN user community are involved, and even more will join in the future when IDA Innova will be approved. The program was initialized a bit the scope because of the reduction of the budget, but additional resources will be looked for. And well, the first fellows and students are already taking up their work, and we started already with some delay because of the COVID-19. Thank you for your attention.
Thank you, Esteban. Are there questions or comments for Esteban? Okay, I see a few residents. Elizabeth, please, Locci.
Yes, thank you. Hi, thank you for this summary of the R&D program. I understood from the new European program, but that could be a revision of this R&D program. Could you comment about that?
Revision, you mean in which way?
Perhaps including more innovative things, because that actually, these are, as you said, techniques that we know CERN already masters, and they are developed for the needs of the future experiments. But there are some new techniques which are promising, but must be developed for the future. Because actually we have to work for something which will happen in 20 years, even more from now, from what concern FCC-HH, for instance.
Yeah, this I was not aware, but I guess it will depend on the budget, because yeah, now we had like a reduction of the budget. Just what it was the initial plan. We cannot now like achieve it, so we had to reduce some activities. But I'm sure that if the budget is increased, for sure it will be include more activities. But so far I don't know about anyone that will be included.
Yes, it's very new actually. We have known the new strategy only 1 month ago, basically. So I think that all that has to be discussed in the next few months, depending also on the situation, the general situation, I guess.
Yeah, I agree.
Thank you.
Elizabeth, we have another question from Andrew White. Please go on. And then
Yes,
another one by Michael.
Could you comment on the relation between these work packages you've described and the current RD programs? Like, what's the relation between the gas detector work package and RD51?
Oh, I think I cannot comment on this one, because I'm just involved in the work package related to silicon detectors, and I'm not the person to comment on this.
Okay.
Sorry.
But there is an RD program for silicon also. What's the relation?
Yeah. Like, for example, for the silicon detectors, I can tell you that we work in a very close environment, but some activities are overlapping. Like some activities that we do in RD50 are as well included in this R&D program. Like, this has to be like this.
Okay, thank you.
I'm not hearing you.
Sorry.
Oh, me? Okay. So this is Michael Marszewski from Prague. I have a question. So you were talking about the R&D in the monolithic detector in the 180 nanometer technology. I assume you mean TowerJazz. Have you given any serious evaluation of the other technologies, like, for example, XFAB 180 nanometers SOI?
Sorry, I'm not an expert on these electronic things. Sorry, I don't know if there is somebody here that works in this work package, but sorry, I cannot answer this question.
Okay. Hi, this is Carlos speaking. I can answer that question.
Okay, yeah, thank you.
Please go on.
Yeah, so indeed we evaluated other foundries, but the reason we are going with TowerJazz is mainly expertise that has been created at CERN around this foundry, right? So, and also the opening of the 65 nanometers to CERN now. So these are basically the reasons why we are choosing TowerJazz at this point in time.
Okay, primarily experience. Okay, thank you.
Okay, let's take the last question from Michael Foley. Don't want to. Michael?
Good afternoon, Foley, Incom. So I had a question about your R&D activities and detectors. Do you have any plans to look at LAPPDs?
This I have no idea right now. Sorry.
Okay, no problem. I know we've worked with many other programs, and I actually give a talk tomorrow morning. However, I figured I'd ask the question now, but thank you.
Okay.
Okay, we should move on to the next talk. Thank you again, Stefan.
Okay, thank you.
Nice talk, was able to trigger a nice discussion. Next talk is from Massimo Casarsa from INFN Trieste. We'll talk us about detector performance study at Muon Collider. I can see your slides.
Great. Good afternoon to everybody.
Okay, please go on.
So, among the envisaged future accelerators, the Muon Collider represents a unique machine which can give access to the multi-TeV energy regime through leptonic collisions. This is very important since differently from what happens in hadronic colliders, in muon collisions, all the center of mass energy is available for the short distance processes. And this opens the way to a tremendous physical potential, which spans from direct detection of new states to the measurement of the higher order terms of the X potential at an unprecedented precision level, and measurements of the standard model processes, of course. Here I just report one example of the many theoretical studies. I took this from a recent publication by Costantini et al. And here the reach of a PP collider is compared with the equivalent reach of a muon collider for the production of a new state via neutral current annihilation of two muons or partons. The message to take from this plot is that to get the same level of cross-section that we have at a muon collider, a PP collider has to pump in much more energy. And this is due to the fact, which I mentioned earlier, protons are composite particles, so only a fraction of the colliding energy participate in the reaction. And considering different benchmarks, the factor of energy in the PP, the higher factor of energy in a PP collider ranges from 3.5 to 5 times that of a muon collider. Unfortunately, such a great potential doesn't come for free. Muons are unstable, and beam muons decay all over the ring. The decay products interact with the machine elements and produce an intense flux of secondary and tertiary particles, a fraction of which eventually reaches the detector. The amount and characteristics of these beam-induced backgrounds depends on the collider energy and the machine optics and the lattice elements. The two main features of these background particles are shown on the three plots on the bottom. On the left, we have the PT spectra. These particles are characterized. Okay, the composition is in order of abundance. We have photons, neutrons, electrons, and charged hadrons. There is a small component of muons which is not shown on these plots. In general, the spectra are very soft. The average energy for the electromagnetic component is around 5-6 MeV. For the hadronic component is half a GeV, and for muons, those are a little harder. It's around 10 GeV. And nonetheless, the amount of these particles is huge, so the tails are not negligible. The second feature is represented by the timing. These background particles are completely asynchronous with the bunch crossing. And so if we consider the time of arrival to the detector with respect to the bunch crossing, we see there is a fraction of background particles which arrive more or less on time, but there is a long tail of stable particles in particular, which arrive hundreds of seconds later. And this represents a very useful feature for the design of a particle experiment. Further details on this topic may be found in a contribution which is scheduled, I think, just now by Francesco Collamati in the accelerator session. So when designing and building an experiment at a muon collider, the name of the game is to deal with the beam-induced background in order to fully exploit the potential provided by a muon, the physical potential provided by a muon collider. We are tackling this, I wouldn't say problem, this challenge on many fronts. One is a suitable machine detector interface design and interaction region design. One is an optimized design of the detector itself, which includes dedicated geometry, high granularity, and timing at any possible level. Then on the reconstruction and analysis side, we think that a crucial role will be played by innovative algorithms based on artificial intelligence or machine learning. In the following, I will report on our findings on our first preliminary study on the effect that the beam induce on the detector response and detector performance. The study is based on a detector full simulation plus reconstruction tools provided by CLIC's ILC soft framework. And the background for a 1.5 TV machine has been generated by Nikolai Mokov with his Mars 15 software for the US muon accelerator program. So the detector we are using is shown, is summarized in this slide. It comprises a full silicon tracker close to the interaction region with a vertex detector with 25 by 25 size pixels, an inner detector and an outer detector with 50 by 50 pixels. Around the tracker, we have an electromagnetic calorimeter with a very high granularity. It consists of 40 layers of tungsten absorber plus silicon pad sensors. Around the electromagnetic calorimeter is the hadronic calorimeter. 60 layers still is the absorber, and the sensitive part is plastic scintillator. Then all of this is immersed in a 4 Tesla magnetic field, and in the outer part we have the iron return yoke of the magnet, in which the muon RPCs are interleaved. Basically, this is the CLIC's detector, but for two differences. We borrowed two of the solutions to which the map studies came to mitigate the beam-induced background. The first is the insertion of two cone-shaped tungsten shields inside the detector around the beam pipe. This is very effectful. It reduces the flux of background particles entering the detector by roughly 500. But as you can see, the drawback is that the nozzles affect the angular acceptance of the tracker. The angle is 5 degrees, 10 degrees, sorry, and it has been optimized for the collision energy of 1.5 TV. We expect that this is going to change for higher collision energies. The second improvement we borrowed from maps is the geometry of the vertex detector. It is shown in cylindrical coordinates in this bottom plot. We have a barrel with 4 layers and cylindrical layers and 6 discs. The gray area in the bottom represents the distributions of the Z-code.
Massimo, you have 2 minutes left.
Okay, 2 minutes left. Okay, so I go ahead. The approach we are using to mitigate the beam-induced background for the tracker is to utilize the timing information. We realized that reading out only hits compatible with particles coming from the interaction point within a very narrow time window, we can reduce the background by a factor of 1/3. And on the bottom right plot, the occupancy is shown, the density of hits in the tracker for the different layers. Other options we are exploring are the measurement of energy deposited in the tracker sensors and correlating the vertex detector as double layers, so correlating the hits in the 2 layers of the detector. Performing the tracking on a full background event is very expensive from the point of view of computational resources. So for the time being, we are performing tracking in theta regions, in 10 independent theta regions. And the result has been tested on a muon sample. The efficiencies as a function of PT and theta are shown on the bottom. Of course, this is not the final point, but it's just the beginning. And here in the theta efficiency, we can already spot a couple of issues. A very steep drop of efficiencies for low theta angles, and a ripple in the efficiency, which correspond to the angular gap between the barrel vertex and the vertex discs. All these are points which we are planning on addressing in future studies. If we compare the performance of the track reconstruction in a sample of muons with and without the beam-induced background, this is what we get. In general, we see that PT efficiency is good, but for a steep drop in the case of background superimposed to the signal in the below 1 GeV. In the theta range, you see that in the central region, apart from small ripples which correspond to the boundary between the...
Sorry, Massimo, you should try to wrap up your talk.
Okay. So as for the calorimeters, again, will play a crucial role in mitigating the background, the timing, and the high granularity. The high granularity and very fine segmentation, longitudinal segmentation, will allow to reconstruct the shape of the showers in the calorimeters and distinguish between background, which releases most of the energy in the first layers, and some signal. Considering the higher level physics reconstruction is not trivial, so we will need particle flow in the jet reconstruction, and objects like photons or electrons, which rely on calorimeter information, will profit a lot from very smart pattern recognition algorithms, which will use the verifying granularities of these calorimeters. So to conclude, a muon collider would represent a unique machine with an extraordinary physics potential. Of course, it poses some unprecedented challenges, both on the experiment and the machine side. On the experiment side, we are very confident that exploiting a thoughtful design of the detector and utilizing recent cutting-edge detector technologies and novel reconstruction and analysis techniques, which are not far away in time, but are being developed just now for the LHC upgrade. So we are thinking of profiting from all these developments. And I also think that the muon collider environment represents a very good test bed for all these new and innovative algorithms. So exploiting all this, we think that it's possible to get a huge harvest of physics results from a muon collider. To get an example, I invite you to attend Lorenzo Sistini's talk on X physics on Friday at the X physics session. Thanks.
Thank you, Massimo. We ran out of time, so are there burning questions for Massimo? Okay, if not, we should move on.
Thank you.
You're very welcome. So next speaker is Jaroslav Adam from Brookhaven National Laboratory, who will talk us about the preliminary design of the interaction region of the Future Electron-Ion Collider, EIC, at BNL. I can see your slides.
Hello, could you hear me?
Yes, please go on.
So thanks to organizers for the opportunity to talk here about the interaction region for the Future Electron-Ion Collider, which will be built at BNL. Okay, so the EIC, Electron-Ion Collider, will evolve from current track. So we'll reuse ion and proton beam from existing crack, and this will allow us to accelerate ions up to uranium, and we'll be adding to it polarized electron beam with energies from 5 to 18 GeV. So this will give us center of mass energy ranging from 29 to 141 GeV, and we want to achieve very high luminosity depending on center of mass energies and ion species up to 10 to the 34 per centimeter square per second. So this will be very first polarized collider of electrons on ions. So the physics interests include spin structure for hadrons, parton distributions, and physics of gluon saturation. And the interaction region where the beams will collide is a very critical part, both from the point of view of collider design and for the detector. So the layout of the interaction region, the IR, is shown here. The task we want from this is to first focus the beams to collide in the middle of the detector, and then separate them to their beam lines. So this interaction region, as is planned now, is where now the star detector is. It gives 9 meters of free space for central detector and has auxiliary instrumentation either in a forward direction, which is proton going side, where there is instrumentation for scattered neutrons and protons, and on the backward side, where electrons are going out, there will be devices for luminosity measurement and a detector for scattered electrons. So there is much more requirements on the IR. So not only to give space for main central detector, but we need also dedicated instruments for specific phenomena which take place along outgoing electrons and outgoing hadron beams. So first, we need to detect scattered protons at very small angles, which will put constraints on exclusive processes. And the task is to achieve PT acceptance from 0.2 to 1.3 GeV. Then we need to detect very forward neutrons, which come from nuclei breakup, and it gives important signature for exclusive processes in electron nucleus interactions. And here we assume to detect neutrons in cone up to 4 millirad. And on the side of outgoing electrons, we need to detect scattered electrons, which is necessary to measure the Q square of the process. These electrons at very low angles are detected after they come through the first beam magnets. And we need to get Bernstein photons whose rate will give us the luminosity of the collider. Yes, to achieve very high luminosities, we need to put the beams at some crossing angle. So the optimal value is crossing at 25 millirads, which allows to make very short spaces between two neighboring bunches and avoids parasitic collisions in bunches which are not supposed to collide yet. So for that, we need specific resonators called crab cavities, which rotate the benches so that even when the beams have a larger angle, the rotated benches collide like it would be head-on collision. And thanks to this, there is no need for bending magnets along central direction, which makes minimal synchrotron radiation imposed on the central detector. So the interaction region itself consists of about twin dipole and quadrupole magnets specialized to individual tasks to form the interaction region. And also these first dipoles on both electron and hadron outgoing side also make spectrometers for scattered electrons and scattered hadrons. So an example is B0 magnet, which acts as spectrometer for protons in forward direction. And on the opposite side of electron side, the first magnets are quadrupoles, which have to handle synchrotron radiation moving along the electron beam. Okay, so coming to interaction region in forward direction, which is direction where protons or nucleons are coming out from the interaction. And electron beam is moving towards the central detector. Here we need specific instrumentation, so-called Raman pots, to detect scattered protons, and 0-degree calorimeter for scattered neutrons. And the placement is driven by requirements on individual magnets, so the area is quite crowded. And also we need to take into account expected beam envelope to tell how close we can go with the detectors to the beam. Okay, if we have a full giant model for the forward region, starting with B0 detector, which is a silicon detector, which detects protons at intermediate angles from 6 to 20 millirads, and is composed of tracking layers just inside B0 inner volume. Then we have of momentum detectors for specific proton kinematics from nuclei breakup. And in the far region, we have Raman pots of silicon tracking layers for protons up to 5 millirad, and 0-degree calorimeters for neutrons, aimed for neutrons at very small angles to 4 millirad. So this ends the detectors at 30 meters from a nominal interaction point. Okay, now coming to interaction region in the rear direction where electron beam is going out of the interaction. So there is challenging load of synchrotron radiation which moves along the electron beam, and here we need instrumentation to measure luminosity, and we need to detect scattered electrons at very small angles. So these are the electrons which go through the first 3 magnets before they are detected. Okay, so we need these photons to measure the luminosity, which is based on Bethe-Heitler-Bremsstrahlung, which gives a very large cross-section in millibarns, shown here for several EIC energies from the top to the lowest energies. And these photons are collimated in a very narrow angular cone. So we see the parametrization and the effect of angular divergence of the beam. And for this, we measure either convergence of these photons to photon exit window, and then we detect electron-positron pairs on a spectrometer detectors for precision measurement of the luminosity. And we detect also non-converted photons which just go through the photon exit window to direct photon calorimeter to address instantaneous performance of the collider. We have also full giant with all essential components on the reader side where the electrons are outgoing. So here the Bremsstrahlung photons are incident on exit window made of aluminum, and then non-converted photons go to photon detector with a graphite filter against synchrotron radiation in front of it, and conversion pairs split in a dipole magnet, and electrons and positrons move up and down to spectrometer detectors. So here in blue are the beam magnets through which the scattered through which Bremsstrahlung photons and scattered electrons go. Okay, and to detect scattered electrons, we are just looking to opposite side of the model, opposite to the components of luminosity detectors. And we propose two tagging stations, tagger 1 and tagger 2, for scattered electrons at different kinematics intervals. So this will achieve with this we will achieve acceptance for Q square below 0.1 GeV square down to basically kinematics limits on scattered electrons. Here, this electromagnetic calorimeter ICL is part of a central detector, and where we have uniform solenoid field of 3 Tesla. So in gray, this is just drift space.
Jaroslav, you have 2 minutes left.
Okay, thank you.
Welcome.
And these drift spaces in gray are transparent in the model. To measure actual Q square with electrons tagging, we need both information. We need to reconstruct scattering angle for the electron, and we need to measure its energy. And together with energy of electron beam, we get the virtuality of the event measured by electron. And so we need for the tagger to measure the energy, and also we need it to make a position sensitive to be able to reconstruct the polar scattering angle. Okay, just to summarize, we have ongoing study to design interaction region and to accommodate all challenges imposed by technical and physics requirements, because EIC will truly go where no one has gone before. Thank you.
Thank you, Jaroslav. Are there questions or comments for the speaker? I don't see raised hand. I have a curiosity. What is the time scale of such a big project?
In about, it's to be completed in about 12 years since now.
But the construction already started or not yet?
Not yet. Prototyping for detector technologies started. And actually STAR will be running for till 2025, also with S-Phoenix.
Okay, I see. Thank you. More comments or questions? I don't see raised hands, so we can move on. Thank you again, Jaroslav. We can move on to the next speaker, who is Andrew White from University of Texas, Arlington, for the SEED consortium. Yes, will tell us about the SEED detector for the International Linear Collider. Please go on.
Okay, thank you for the opportunity to talk about the SID detector for the International Linear Collider. So let me begin with a few words about the ILC itself. This is a fairly mature electron-positron collider designed particularly for the initial 250 GeV stage. There have been a lot of studies carried out on this over the last 10 years or so. I've, for completeness, given some of the collider parameters here. We have run scenarios you can see on the bottom left to cover the physics program. We have a site for the collider that's being studied in the Kitakami Mountains and the upper regions of the large island of Japan. The physics is being covered by other talks in this conference, but I give an example of the Higgs couplings and reaching down to percent and below levels for the precision on these couplings. At the moment, we're about to go through a transition to a development team, which will exist for a year or so. And then from early 22 onwards, we will be into a stage of the pre-laboratory, which will then lead after 4 years to the ILC lab itself. The ILC has recently received quite a bit of publicity and support. The European strategy highlighted the ILC in one of its main statements. We've had a lot of support from the highest levels of the Office of Science in the US in terms of ILC as a part of a global science program for the US. And the US Office of High Energy Physics at DOE has, amongst other agencies like the State Department, OSTP, and National Security Council are supporting this initiative. And so, as I said, we expect even next week to move into this next phase to set up the pre-laboratory. So moving on to the SID detector, this design has been around for quite a while. It's been validated by an international group, and it's been shown we can deliver the ILC physics program as it's currently understood. We have a consortium to study this detector that's also been around for a while. We have a light set of bylaws. We have individual and institutional memberships, and particularly guest memberships, which for people who want to do snowmass studies. And I want to emphasize throughout this talk that we're very open and welcoming of new colleagues to join and contribute new ideas or upgrades, alternatives, and we're particularly anxious to have young people join. The physics requirements for the SID and the ILC physics program are by now well understood in terms of what we require out of the vertex detector, the main tracker, the tracker and calorimeter working together for the particle flow, and specialized studies, for instance, for SUSY. So those physics talks items are covered in other talks. So the baseline detector has an all silicon center, both for the vertex detector and the silicon strip tracker. That's surrounded by an electromagnetic calorimeter, also using silicon readout, surrounded in turn by a hadron calorimeter. All of these elements are then contained within a 5 Tesla superconducting coil, which itself is surrounded by a return yoke and muon chambers. You can see some of the mechanical arrangements here, the cartoons on the right. Our design rationale has been to have a compact, cost-constrained detector, which will just be designed to make precision measurements, particularly of Higgs couplings, and be sensitive to a wide range of new phenomena. We feature a robust silicon vertexing and tracking system with excellent momentum resolution, live for single bunch crossings. We have highly segmented so-called tracking calorimeters optimized for particle flow. We have a compact design which requires a high central field at 5 Tesla, and the iron flux return is instrumented as a muon identifier. We've also been studying this in terms of one interaction region for rapid push-pull interaction region operation if necessary. So to go through the components quickly, the silicon vertex detector has 5 barrel layers and forward disks. We have some preliminary mechanical design ideas for this. It features power pulsing, forced air cooling. It has pretty challenging requirements in terms of hit resolution. Material needs to be kept to an absolute minimum, power requirements down, but we feature power pulsing to help with this, single bunch time resolution. And for instance, we've been studying the intense pair backgrounds and the sort of stay clear region for the inner layers of the vertex detector. This 5 Tesla field allows us to have the first layer very close to the beam, for instance, at 14 millimeters. One instance of a possible vertex detector design is the chronopixel from Oregon and Yale. This has gone through a number of prototype studies. I show one instance of this here, so-called option 3, a shallow N-well configuration. This has been a multi-year development of this, and it has been shown that this CMOS vertex sensor arrangement can satisfy the IOC design requirements, as you can see in the table on the bottom right, comparing IOC requirements with the prototype tests. We also have some other possible alternatives using vertically integrated 3D arrangements, high voltage CMOS for good timing, etc. So there's plenty of opportunity here for collaboration. Moving on to the central tracker, this is silicon silicon strip tracker in the baseline using a 25 micron pitch, 5 barrel layers and 4 forward disks. This, when it's unified with a vertex detector, gives us 10 layers of tracking. It's gas cooled. It has low material budget. This is read out by the KPIX 1024 channel ASIC designed at SLAC, which also is used for the electromagnetic calorimeter. You can see some of the designs here on the left-hand side, the arrangement of the layers. This arrangement will give us excellent momentum resolution, for instance, in recall mass studies. You can see the low material profile at the bottom right. There have also been initiatives to design a MAPS pixel-based tracker with a new version of the KPIX to go with this. So this is being pursued between SLAC and DAISY, and there's again opportunity here for collaboration. In DAISY, there have been some beam tests of the silicon strips. You can see in the top center these KPIX chips reading out the silicon sensor. We've shown the charge distribution for the hits on the track and shown pretty good single point resolution. The electromagnetic calorimeter is a highly granular imaging calorimeter essential for this particle flow program. It has an aggressive design. On the middle left, you can see that there is a 1¼ millimeter gap for the active layers between the tungsten plates. The sensors at the bottom left feature the 1024 pixels of 30 square millimeters each. This is matched to the channel count for the KPIX readout. So far, there's been a 9-layer test at SLAC. You can see an example of a single electron event on the bottom right. More from the tests here, we've shown a good signal amplitude, excellent 2-electron separation, top right, good agreement between the 1 and 2 electron events and what is expected for a simulation. There were some issues with some crosstalk of signal lines crossing the sensor elements. This has been addressed with a new sensor design, new cable design. And now we're into testing of the new sensor bonded to the KPIX. And again, here, there are opportunities for people to work on this. The hadron calorimeter features this 12-fold geometry. The baseline is following the CALICE, so-called AHCal analog HCal design. This, for instance, is very similar to the CMS HGCal scintillator components. So we are members of the CALICE collaboration and closely following that design. We have some mechanical design specific to the IOC detector for this particular technology. What we've been doing is to actually take the CALICE design, map it onto SID, and then study the performance of 40 layers for single particles, compare that with the energy resolution obtained from the CALICE AHCal test beam, which compares favorably in this case, as you can see on the bottom right. We have forward calorimetry, there's a luminosity calorimeter you can see, and a beam calorimeter, which is done, gives us hermetic coverage down to very small angles. Also on the top left here, you can see that the L star is at the commonly agreed 4.1 meters between SID and the other detector ILD. The forward calorimetry, beam cal gets 100 megarads per year, so there's a great requirement here to study radiation effects. This has been carried out over a period of time by Bruce Schumann colleagues from Santa Cruz, working at SLAC and test beam. They've done high-level exposures both for the silicon diode sensors, you can see here on the top right. They've also studied some gallium arsenide sensors. And there's more work to be done here, but the silicon diodes in particular have been shown to be still active and usable after a high level of exposure. We've also done studies for the machine detector interface. For instance, the beam delivery system muon study here. If you don't pick some mitigation strategies, then you would have a high flux of muons and unwanted hits in the detector, as you can see on this picture on the right, all these extra hits. So one has the option, for instance, of installing magnetized spoilers or a magnetic wall.
Sorry, Andrew, you have 2 minutes left.
Okay, thank you. So it's been shown by Anna Schütz from DAISY that for the initial 250 GeV of collision energy of the ILC, that the magnetized spoilers are okay, but if we move to the higher energies, we might have to include this magnetized wall also to keep down these unwanted hits. The SID solenoid itself, the 5 Tesla solenoid, the baseline follows the CMS conductor pattern. We had a redesign from a 90-degree split between the barrel and the end cap to 30 degrees. This has the benefit of having more efficient flux return, easier large pieces to handle for the flux return, and it also satisfies the Japanese safety requirement of less than 50 Gauss at 15 meters from the detector. We also, bottom left, have an idea of how all this large coil would be assembled into SID. I included some more pictures here from Marco Uriuno, who's been doing some of the preliminary mechanical design with this 30-degree angle. The muon system itself would be instrumented with long scintillator strips with wavelength shifting fiber readout, read out by SIPMs. This has been studied by colleagues at Fermilab for different arrangements of the tile and fiber configuration, and satisfactory results have been shown for both the time resolution and the position resolution to match the ILC requirements. Just a word about snowmass. There is a document from the LCC Linear Collider Collaboration Physics Working Group led by Michael Peskin and others, which has posed a large number of physics questions to be addressed at snowmass. For SID, we actually have a primer on ILC physics and SID software tools, and we're making Monte Carlo samples available, and we're very keen for people to get involved with this. We try to make this, the entry into these studies as painless as possible. So to conclude, the ILC itself and SID collaboration are going forward. The ILC is moving towards realization. This international development team is expected to be in place starting next week after ratification by ICFA. SID has a validated detector design that can deliver the ILC physics program. There are many opportunities for new ideas and optimization of design. We welcome new members. Join us for the snowmass studies and beyond, of course. And especially if young colleagues are listening, we're very welcoming for you to join us. If senior colleagues are listening, please keep this future option over as a major opportunity for your young colleagues. Thank you for listening.
Thank you, Andrew. Very nice talk. Comments or questions for the speaker? I don't see raised hands. Just for my education, as we have seen, also at CERN there is a big effort in designing and planning new detectors. What are, if they exist, the point of contacts with the development for future detector at CERN with your program?
Well, we've had quite a bit of a high level of collaboration between people designing ILC detectors and the click detector, for instance. We have some common software, and we've had a lot of collaboration over the last few years in that direction. Less so with the FCC EE, but certainly with click.
Okay. Thank you, Andrew. Thank you again.
Thank you.
We can move on and go to the last talk of the session. The speaker is Adriano Giovanni from New York University in Abu Dhabi. For the Light 1 collaboration, we will talk us about RedSat, a CubeSat mission for the detection of terrestrial gamma ray flashes. I can see your slides, Adriano. I cannot hear you. Yes, I can
Oh,
hear
yes,
you.
yes, I wasn't talking, yes. I wasn't speaking. So thank you, Ettore. First of all, it's a pleasure to be here and to see you as convener of the session. And thank you all for staying with me for the last presentation of the day. So I'm going to talk about a CubeSat space mission targeting terrestrial gamma ray flashes. So it's something that is a bit off topic, but I hope to trigger some interest in some of you. So I will give a brief introduction about CubeSat terrestrial gamma ray flashes. We'll briefly go through the scientific and technological goal of the satellite, a quick description of the payload, and then a preliminary simulation of the first 5,000 seconds of the mission. So CubeSat, it's really a new paradigm for space mission, essentially because their cost. So usually a CubeSat mission costs less than $1 million. That is something relevant in space missions. It's a modular object. Each unit is a sort of a cube, 10 by 10 by 11 centimeter. And then, of course, you have to deal with the weight, space, and power, and also data transmission constraint given the size of your detector. The launch cost is usually cheap because you do piggybacking, so you put your detector to fill the voids left from other missions, and so the system can be deployed either from the rocket itself or brought to the International Space Station and deployed from the International Space Station. That would be our case. So terrestrial gamma ray flashes, in general, those are a prompt emission of gamma rays. By the way, it's the most intense phenomena involving gamma ray occurring naturally on our planet. So the idea is that whenever you have a intense thunderstorm, so the lightning can create an intense electric field and accelerate electrons. So these electrons are moving in the environment of the atmosphere. So you can have some Bremsstrahlung emission. So these gammas comes from the Bremsstrahlung. And then you can also have other different counterparties like electrons from the pair production of a fraction of this gamma, neutrons from the photon production, and also radio emission. So the main feature of a TGF is the energy range. So the gamma emission is between 10 keV up to hundreds of MeV. And TGF has a quite distinctive time scale that is of the order of hundreds of microseconds. So if you are orbiting on a LEO orbit, a low Earth orbit, let's say 400 to 500 kilometers from Earth, and you are lucky and you are on top of a TGF, you should expect something like 1 gamma per square centimeter of detector. So these TGF were detected by several satellites tuned for other physics, like looking for gamma ray bursts. And to date, there is only one experiment that is mounted on the Colombo platform on the International Space Station that is taking data and is designed to detect terrestrial gamma ray flashes. So a few other hints about terrestrial gamma ray flashes. We know more or less where the TGF happen, not when, but where, because most of the thunderstorm happens on the equatorial line. So if you have a satellite orbiting with a polar orbit, you actually cross the equator many times per day. So the probability to get some TGF becomes relevant. Scientific and technological goals of our mission. So we want to study the TGF down to sub-microsecond time scale that is incredibly challenging for a CubeSat mission with the constraint of a CubeSat mission. We want to try to measure the intensity of the radioactive intensity in the South Atlantic anomaly region, and of course to space qualify and prove the detection, space qualify the technology, improve the detection concept in view of a possible constellation of CubeSat targeting terrestrial gamma ray flashes, gamma ray burst, and also being able to perform some multi-messenger physics. And of course, this the idea is that this satellite needs to survive to the launch, to the deployment from the SSS and from the environment. Several characteristics of the detector. So the energy threshold is of about 20 keV. We have a nice time resolution of the order of 200 nanoseconds. That will give us the possibility to have an absolute timing of 2 microseconds. This is useful if you want to correlate your detection with existing catalog of TGF. We'll do everything we intend to do with 4.5 watts in average, and we can download about 50 megabytes of data per day. So the orbit is the orbit of the International Space Station, because the system will be deployed from the International Space Station. So that's our satellite. It's a 3D model, of course. So it's 35 centimeter long, 10 by 10 cross section, and we have 2 payloads. So we identified the first payload with photomultiplier payload, and the second payload is the silicon photomultiplier payload, because we are using 2 different sensing technology. And then we have all the other subsystems needed for the mission, such as the rotating wheels to maintain the aspect of the satellite, the electrical power system for the power, the receiver for streaming the data, and also the UHF antenna for the housekeeping data. So if you open the payloads are 2 compact objects, the PMT payload, the CPM payload. So in total, the total weight of the payload only it's 2.2 kilograms. And if you open the box on the left, you will see something like that, in which, so in green, we have the controller board of the payload plus the readouts needed to read out the signal, of course. So if we, so let's have a closer look. Both the payloads are equipped with a VITO system that we use to reject charged particles. And of course, the PMT payload as PMTs, while the CPM payload makes use of multi-pixel photon counters from Hamamatsu. That's a screenshot of the VITO device. Basically, we have 8 channels. Each channel is composed of a plastic scintillator tile, a wavelength shifter fiber, readout by an advanced silicon photomultiplier tube. And we use this system only to tag charge-induced events, because in principle, we don't expect gamma to trigger many times the VITO. We already have an idea. So it's more or less 7% of the time we also have a fake event induced by the gamma. So inside, the detection unit is basically a crystal, four independent, optical independent units. Each unit is read out by its photosensor. And so a few words about the photosensor. So we decide to use 2 different technologies, essentially for 2 reasons. One, we want to space qualify the 2 different technologies. So a compact photomultiplier tube and a multi-pixel photon counter, both from Hamamatsu. And then there is also the reason that we have to deal with the space and mass constraint of the satellite. So the CPM is much lighter and compact than the photomultiplier tubes. But of course, we have the drawback that the CPM is an incredible source of dark counting rate. So we need to deal with that. The target is a crystal, so it's a segmented crystal, 4 independent units. The 2 arrays are slightly different. The first one is made out of 4 cerium bromide crystal. The other one is an hybrid configuration in which we have 2 cerium bromide crystal and 2 lanthanum bromochloride crystals. Again, we want to space qualify both the technology, and also we want to exploit, if possible, the better resolution at the low energy of the lanthanum bromochloride crystal. So we move now to the simulation that we are performing. So the idea is to actually simulate the detection strategy. So we have a GN4 simulation that actually produces the interaction in the detector, and then we have the signal simulation that translates the energy deposited in the detector into signals. So the other objectives of the simulation.
Sorry, Adriano, you have 2 minutes left.
Okay, so to estimate the detection efficiency, the other threshold, because we have a lot of shielding from the other subsystem of the satellites, to assess the charge particle rejection capability, to create the background model of an orbit, and also to assess the discrimination capability of a TGF with respect to a background sample. So to make the long story short, the ingredients for the background model are essentially two. We have extragalactic photons measured by the Fermi mission, and we expect to have this extragalactic photon coming isotropically from all the direction, with the exception of the phase looking at the Earth, because of course the Earth will offer a shielding. And then we also have the trapped charged particle components, and these profiles can be actually obtained by running a simulation with SPANPIS, that is a software devoted to this kind of analysis and developed by the European Space Agency. So in a few words, that's the sample of, so counts as a function of the energy of our background. So, and inside this background, we actually added a TGF, a real TGF as the agile emission. So that's our detector in GM4. That's our background. So we have 200 Hertz over 5,000 seconds of emission, and then we, based on the simulation that we performed, we establish a set of cuts to reduce the data. It's I mean, the easiest cut that you can think of. It is relevant, the cut number 5, because it contains the signature of a TGF event. So an high rate in a very short time. So, and if you apply all these cuts, you can reduce your data, and then actually you spot the TGF, and this actually is the TGF from the eye of the electronics. So in this particular event that lasted 175 microseconds, at the source we had eight gammas. 2 of them got lost, either absorbed by the shielding or simply went through the detector, and 6 of them were absorbed just by chance. So all the absorbed were detected by the 2 detectors looking at ground. So the idea is that if you count the number of peaks, that's the role of the matching filter on the FPGA. You should actually reconstruct the number of photons that interacted. So we have 1, 2, 3 on the channel 3, 1, 2, 3, 4 on the channel 4. So it means that we had 7 detection. But if you superimpose on the time the waveform of C3 and C4, you realize that you actually had a Compton effect. So a gamma, it's channel number 3, Compton effect, enters channel number 4, again a Compton or a full absorption, and then you see this event on both of the crystal at the same time. So that's I'm quite happy of this capability we have, because this is proving that we actually can do some real science with a very small object. So conclusion, we aim at detecting terrestrial gamma ray flashes either by ourselves, so measuring the events, or looking at the catalog of other experiments and just cross-check with the, since we have a nice time, absolute timing, so we can actually cross-check with the other catalogs. But then the real point is to space qualify the technology and prove the detection concept in order to be able to propose a constellation of such kind of detector. So the payload would be assembled this September. And the launch is scheduled for the second quarter of next year, so in 1 year. And then this is the other feature of CubeSat, is much faster. So the procedure is much faster than a standard satellite space mission. And so last but not least, this satellite will be the first particle detector payload built and operated in the United Arab Emirates. Thank you very much for your time and attention.
Thank you, Adriano. Are there questions or comments? Yes, Michael, please.
Yes, thank you for a nice talk. I have a few questions. So since these scintillator crystals we are using, they have quite a high density. What is the total weight of your payload?
Yes, so the payload is 2.2 kilograms. So it's basically, so the PMT payload is slightly more, it's heavier than the CPM payloads.
Yes, so
essentially because you have PMTs.
And what is your power consumption? Because for free, you can have something like 3 watts, right?
It's in average is 4.5 watts, while the consumption of the entire satellite it's around 9 watts.
So you can operate only part of the time, right?
We will be operating. So the duty cycle it's like 60%, and it's fine because we know that most of the TGF will happen on the equator and will cross the equator 19 times per day. And also we have to switch off everything when we are about to enter the South Atlantic anomaly. That is this region in which the magnetic field is weak. And then you have an increase of protons and electrons that can actually be harmful for your detectors.
Yes, and my last question concerns how does your discrimination against cosmic gamma ray flashes work?
Yes, so it's the time scale. It's basically a time scale. So okay. a gamma ray burst, the typical time scale is about it's several seconds, while a TGF is of the order of less than 1 millisecond. So, and it's a distinctive signature.
Typical signature, so you get the signal from this runaway acceleration in higher atmospheric levels. Okay, thank you.
Adrian, I have one more question. How many MPPC do you have on board, and how are you reading them out?
So we have 4 MPPC, and and then I said that it's a cheap mission, so we had to come up with a nice idea to read them out. So the electronic is identical to the electronic that we are using for the photomultiplier tubes, meaning that we'll simply do the OR of each cell, because this model is actually it's 16 cells. But each flash of light will be really bright, so we don't care to preserve the single photon detection capability.
Okay, thank you, Adriano. Are there more questions or comments? I don't see raised hands. Michael, do you have news about the discussion session? Will we have one, and when?
Well, I don't know whether people are interested in a discussion session, but we can do as what we did yesterday, join the tracks number 12 and 13, since we are the same detector community. I think there's possibly more people there, or we can start here and continue there.
Right. I mean, there are few people left here, I see. I will suggest people eventually to join the other sessions. And and the rooms are for the discussion is which is the room for this discussion?
I think yes, I think it's the same room as used for the regular program.
Okay. Okay, so people interested in the discussion should join that the room, and I mean the same password of this section. Okay, I think Michael, we can close the session here. I stop recording.
Okay.
I thank you all the speakers, the people who attended the session. Was very nice. A lot of news, a lot of activities. I want to thank the organizer for